The quiet of the moon's far side. What does silence feel like when there is no one left to break it? On Earth, silence is always relative. A quiet room still hums with electricity. A forest still rustles with leaves and breath. Even sleep is accompanied by the rhythm of a heartbeat. But the far side of the moon, the side that never faces us, offers a silence so pure, so untouched, that even radio waves dare not enter. It is not just quiet. It is a kind of cosmic hush, a perfect stillness untouched by noise or news or need. And in that stillness lives one of the most hauntingly beautiful mysteries of our solar system. The moon is tidally locked, meaning it rotates in such a way that one side always faces the Earth. The far side, often mistakenly called the dark side, receives just as much sunlight as the side we see. But it has lived its life in secrecy. No eye saw it directly until 1959, when a Soviet spacecraft captured its shadow terrain for the first time. What it revealed was something strange. A landscape filled with craters, ancient and deep, far rougher than the one that faces us. Why is the far side so much more battered? Why does it lack the smooth, dark plains the lunar Maria found on the near side? Scientists believe it may be due to differences in the moon's crust thickness. The near side, thinner, may have allowed more lava flows to cover its wounds. The far side, thicker, stayed scarred. It is a face that never learned to heal, and yet, there's more. Because that far side is permanently shielded from Earth's electromagnetic noise, it offers something profound, the quietest place in the inner solar system. If you were to stand there, in the shadow of an ancient crater, and raise an antenna to the sky, you would hear nothing. No human static, no interference. Only the soft, undisturbed whispers of the universe primordial, unfiltered, untouched. This silence is so valuable that astronomers dream of placing a radio telescope there, an observatory shielded by the moon's bulk. Listening not to the stars that scream, but to the ones that whisper, to the remnants of the cosmic dawn, to the ancient frequencies that carry the birth of everything. And maybe, in that silence, something else waits. Not aliens or ghosts or gods, but a feeling, a sensation of absolute smallness, of floating in a place where no one has ever shouted, where war and worry have never arrived. A side of the moon that has watched the Earth's entire history without once being seen. The far side is not dark, it's just quiet. And in that quiet, the moon holds something sacred, a space untouched by human hands or human drama, a side that does not perform, a world that listens even as no one speaks. So tonight, as you drift, imagine standing there, just you, the stars above, a sea of craters beneath, and nothing but the soft hum of your own breath, the only sound for 250,000 miles. Sleep well beneath the gaze of the moon's forgotten face. The great void in Boetes. What if you looked into the sky and saw nothing looking back? In a universe brimming with stars, galaxies, and the glow of ancient light, emptiness feels unnatural. We expect the cosmos to be alive, teeming with radiant clusters and spinning spirals, stretching endlessly in every direction. But in one corner of the sky, nestled deep in the constellation Boetis, lies something almost eerie, a space so empty it seems to defy the laws of existence. It's called the Boetis Void, a staggering cosmic hollow, roughly 330 million light-years across. A place where, quite simply, almost nothing is. It is not a patch of night between stars. It is a true gap in the tapestry of galaxies. If the average region of the universe were a bustling metropolis, the Boetes Void would be a forgotten desert. A stretch of sky where galaxies vanish, where light rarely travels, where something, long ago, failed to form or was somehow undone. Discovered in the 1980s during a galaxy mapping survey, astronomers first thought their instruments were malfunctioning. A void this large, this clean shouldn't exist. The universe is structured like a web, with galaxies clustered along filaments of dark matter and gas, separated by more modest voids. But the Boetes Void was different. It was too vast, too quiet, too precise. Within its enormous volume, you'd expect to find thousands of galaxies. Instead, we find maybe 60. Sparse, scattered, lonely. It's as if a cosmic brush swept clean a canvas of stars, leaving only the echo of what might have been. And this leads to questions that still haunt astrophysicists today. Was this void the result of strange early universe physics? A place where matter never gathered? Or did something more active occur, a repulsion, an expansion, an unknown force pushing everything outward from some forgotten center? Some suggest the void may have formed from overlapping smaller voids, a statistical accident of structure. Others whisper stranger possibilities, imprints from another universe, signs of a cosmic collision in dimensions we can't perceive. And then, there are those who wonder if the emptiness is hiding something. We often think of space as full of mystery, full of motion, full of life. But the Boete's void reminds us that the universe is not afraid of silence, not afraid of gaps. It allows blankness. It permits places where nothing happens. And perhaps, in those places, we feel something ancient stir within us, a kind of loneliness that isn't sad, but sacred. A reminder of how rare we are. How miraculous our own galaxy is, a glowing ember in an ocean of dark. So tonight, close your eyes. Let your thoughts drift into that cold, quiet hollow. Float between the almost galaxies, in the space where light rarely lingers. And feel, for a moment, what it means to truly disappear into silence, not in fear, but in peace. The Boete's void waits with open arms, not to swallow, but to soothe. Saturn's hexagon storm. What if nature preferred shapes even in chaos? We think of weather as messy swirling clouds, uneven storms, scattered lightning. Nothing about it feels precise. Yet above the North Pole of Saturn, a planet known for its quiet rings and silent distance, something impossible happens. A storm with 6 perfect sides. A geometric phenomenon swirling endlessly in a place with no corners. It's called Saturn's hexagon. A 6-sided jet stream, wider than 2 Earths laid side by side, and it's been there for decades, maybe even centuries. First spotted by the Voyager spacecraft in the early 1980s, then studied in detail by the Cassini mission. This shape should not exist, and yet it persists. A hexagon carved into the atmosphere of a gas giant, unmoved by time, untouched by chaos. So how does it form? The current best theory involves differences in wind speed. Saturn's atmosphere flows in layers like bands on a spinning globe. Where fast-moving gas meets slower air, vortices appear. On Earth, this creates storms. But on Saturn, the balance is more delicate. Scientists recreated similar hexagonal patterns in laboratories by spinning liquids in circular tanks. The result? When conditions are just right, nature prefers symmetry. But this doesn't explain everything. Why 6 sides? Why not 5 or 7 or some other unstable polygon? And why does it last unmoving, unbroken for decades? Some suspect deeper forces. Perhaps the storm is locked into place by Saturn's magnetic field. Perhaps the planet's rotation and density create a natural harmony that fosters geometric beauty. Or perhaps the hexagon is simply a whisper from nature, telling us that not all chaos is without structure. When we look at Saturn's pole, we're reminded that patterns can emerge even where we expect none. That storms, even the wildest ones, can wear the face of geometry. And maybe, deep in the gas and wind, there's a kind of quiet intelligence at work, not a mind. Not a message, just an elegant response to motion, balance, and time. There is poetry in the idea that a planet millions of miles away spins with a storm shaped like a crystal. That in the cold, swirling clouds of hydrogen and helium, a hexagon holds its form against all odds. A shape that has no reason to exist, except that it does. It invites us to wonder if the universe, in its vastness, sometimes creates beauty simply because it can. That even where no one watches, elegance arises, not for purpose, not for meaning, but as a side effect of motion, pressure, temperature, and the deep laws that govern everything. So as you rest tonight, picture that shape, 6 sides, spinning slowly at the edge of a world you've never touched. Let your breath follow its motion. Let your thoughts soften into pattern. Let your worries scatter into rings, like those that encircle Saturn's silent song, and sleep beneath the watchful geometry of a planet's perfect storm. Venus's runaway greenhouse. What happens when a planet forgets how to breathe? Venus, in many ways, is Earth's twin. Roughly the same size, made of rock, with clouds and sunlight and a core that once stirred. But something went wrong. Terribly, quietly wrong. And now, the brightest planet in our sky is also the deadliest. A world wrapped in its own heat, where the atmosphere is thicker than oceans and the temperature can melt lead. It wasn't always this way. Scientists believe Venus may once have had water lakes, maybe even shallow seas, a planet not unlike our own, basking in gentle sunlight. But its fate changed as carbon dioxide began to build in its skies. Heat from the sun, instead of escaping, was trapped, slowly at first, then irreversibly. The clouds thickened, the oceans boiled, the pressure climbed. And Venus, once Earth's sister, became a furnace. This is called the runaway greenhouse effect, a planetary chain reaction where warmth feeds more warmth until the cycle cannot be reversed. Venus now wears a cloak of clouds so dense they reflect most sunlight away. Yet beneath them, the planet burns. The surface temperature is over 460 degrees Celsius. The air, mostly carbon dioxide, is so heavy it would crush you before you could even gasp. Stranger still, the clouds of Venus are laced with sulfuric acid. The wind howls at hurricane speeds, circling the planet every few days. It rains acid, but the rain never touches the ground. It evaporates in the heat long before it lands. A storm with no mercy, a sky with no relief. But perhaps the most haunting part is this. Venus started off so much like us. Two planets born from the same dust, shaped by the same star. Yet one learned balance, the other forgot. Venus is not just a hellscape, it is a mirror held up to Earth. A reminder that planets, like people, must learn how to regulate their warmth before it becomes their fire. Some scientists wonder if Venus had a chance if something tipped the balance too fast. A burst of volcanic activity, a shift in solar radiation, or perhaps it was always doomed, destined to cross the point of no return. Its story, hidden beneath clouds we still cannot fully penetrate, remains one of the solar system's great puzzles. And yet, we still look to it. We send probes. We study its skies, because Venus, despite its silence, may hold answers about Earth's future, about climate, about the fragile line between life and heat, between balance and collapse. So tonight, drift gently between worlds. Let Venus be your ghost planet, not a warning, but a whisper. A reminder that even a planet bathed in sunlight can burn. That beauty can become danger. And that sometimes, silence isn't stillness, it's aftermath. Sleep in peace, knowing that our sky, for now, still breathes for us. And may we never forget the lesson written in Venus's flame. The sun's missing neutrinos. What if the smallest things simply vanished when you looked for them? The sun shines with a steady, golden warmth. But beneath its glowing surface, something extraordinary happens every second. Deep in its core, atoms smash together in a fusion of hydrogen into helium, releasing not just light, but something much harder to catch. Neutrinos. Tiny, ghost-like particles that pass through matter as if it isn't there. Trillions of them stream through your body every second, unnoticed, untouched. For decades, scientists expected the sun to produce vast numbers of these neutrinos, and they built detectors deep underground, shielded from noise to count them. But when the data came in, something was wrong. The numbers didn't match. Only a third of the expected neutrinos were showing up. It was as if the sun had lost 2/3 of its particles somewhere on their journey to Earth. This became known as the solar neutrino problem, one of the strangest scientific mysteries of the 20th century. Was our understanding of the sun flawed? Was there something broken in the detectors? Or was something weirder happening? As it turns out, the answer was weirder. Neutrinos, it seems, are not simple. They come in 3 flavors: electron, muon, and tau. The sun produces electron neutrinos, but by the time they reach Earth, many of them have changed. Transformed mid-flight into different types the early detectors couldn't see. This transformation is called neutrino oscillation, and it means that these particles can shift identities as they travel. A behavior that only makes sense if neutrinos have mass, which we once thought they didn't. Their tiny flickers of mass allow them to morph to become something else entirely. It's like throwing a basketball and watching it turn into a tennis ball in mid-air, then land as a golf ball. And so, the mystery wasn't that the sun was failing us. It was that the neutrinos were hiding in plain sight, changing masks, dancing through space in forms we hadn't yet learned to recognize. This tiny puzzle cracked open a door to deeper physics. It hinted at gaps in the standard model, the reigning theory of particles and forces. It whispered of new possibilities, unknown particles, hidden energies, even a deeper symmetry of the cosmos still waiting to be seen. But even if we never solved it, the image is enough to lull us, a storm of invisible particles washing over you every night, quietly humming through walls and bone, whispering of fusion and stars. Each one a messenger from the heart of the sun, shaped by fire, changed by space, and arriving gently, invisibly like starlight for the soul. So tonight, let go of what you can't see. Let the neutrinos pass through you like breeze through an open field. Feel how much of the universe moves without needing to be noticed, and know that sometimes the smallest mysteries are the ones that change everything. Sleep while particles from the center of the sun quietly pass through your dreams. Jupiter's everlasting storm. What if a storm never ended? On Earth, storms come and go. Winds rise, clouds gather, rain falls, and then the skies clear. But on Jupiter, the rules are different. There, spanning for centuries without pause, is a storm so vast and ancient it could swallow the Earth whole. A crimson whirlpool of rage and rhythm, known simply as the Great Red Spot. This storm is no passing thundercloud. It's a permanent scar in Jupiter's southern hemisphere, a swirling vortex twice the size of our entire planet, with winds whipping faster than any hurricane Earth has ever known. It's been observed for over 350 years, perhaps much longer, and it shows no sign of stopping. But why? Why does it last? The answer is not entirely clear. Jupiter is a gas giant, a planet without solid ground. Its atmosphere is layered, vast, and turbulent. Unlike storms on Earth, which lose energy when they interact with land or cooler air, Jupiter's storms have nothing to slow them down. The gas just keeps moving, and the heat from Jupiter's interior continues to feed them. Some believe the Great Red Spot is trapped between powerful jet streams locked in a gravitational and atmospheric tug-of-war that keeps it spinning endlessly. Others think the planet's rotation, faster than any other in the solar system, creates a kind of balance, letting the storm sustain its shape through a combination of chaos and harmony. But even so, this storm should have died, and yet it hasn't. It shrinks, then grows. It fades, then deepens in color again. It pulses with mystery, like the heartbeat of a planet. What's more haunting is the silence. If you could somehow float above the Great Red Spot suspended in the upper atmosphere, just watching, there would be no roar, no thunder. Just the quiet churn of wind in an atmosphere 300 times deeper than Earth's soul. A slow, hypnotic spiral. A dance too large to feel, too old to fear. Its red color remains unexplained. Some say it's caused by chemicals reacting with ultraviolet light from the sun. Others suspect unknown compounds, complex cloud chemistry, or even photochemical smog. But no one knows for sure. Like a wound, it glows. Like a ritual, it spins. And in this endless cyclone, we see the strange poetry of gas giants, planets that do not sit still, that do not age in the way we understand. Their weather is not fleeting, it is structural, ancient, written into the rhythm of their skies. Jupiter's Great Red Spot reminds us that not all storms are meant to pass. Some exist simply to exist, to turn and twist and endure. Not for destruction, not for cleansing, but as a symbol of cosmic persistence, motion without fatigue, power without a scream. So tonight, drift into the eye of a storm that never blinks. Let the spiral lull you, not with fear, but with wonder. Feel the weightlessness of clouds that have no ground. Let go of time, let go of endings, and rest in the calm at the heart of Jupiter's forever storm. Neptune's inverted winds. What if the coldest place held the fastest winds? Neptune lies at the edge of our solar system, a planet so distant it takes sunlight over 4 hours to arrive. It is a world of frozen clouds, icy storms, and deep, dark blues. A planet wrapped in shadows and silence. But beneath that silence rages something unexpected, the fastest winds in the solar system. In a place colder than -200 degrees Celsius, where the sun is little more than a distant star, Neptune's atmosphere howls. Winds whip across its surface at speeds up to 2,100 kilometers per hour, faster than the speed of sound on Earth, faster than any hurricane, faster than reason. It makes no sense. The sun drives our weather. Heat from the sun causes air to rise, clouds to form, storms to brew. But Neptune is far too cold and far too distant for solar energy to explain this chaos. So where does this energy come from? How does a frozen planet create such violent motion? One theory is that Neptune generates internal heat. Deep inside, it may still radiate warmth left over from its formation or from the compression of gases under its immense pressure. This heat could rise through the atmosphere, fueling winds that spiral outward with astonishing force. Another mystery lies in how these winds move. On Earth, wind speed tends to increase with altitude where there's less friction. But on Neptune, measurements suggest something stranger. Some winds travel faster at lower altitudes beneath the haze and clouds. It's as if the planet's atmosphere flows backwards layers, defying our expectations, pressure building where it shouldn't, motion born from stillness. Adding to the strangeness are Neptune's storms like the Great Dark Spot, first spotted by Voyager 2 in 1989. It was a massive storm system, large enough to swallow Earth, which later vanished, only for another to form. These spots come and go, their patterns irregular and unexplained. A choreography of shadows, unfolding without warning, vanishing without trace. It's hard to study Neptune. So far, only one spacecraft, Voyager 2, has visited, and from Earth, its distance blurs our instruments. What we know is drawn from glimpses and guesses. Neptune remains a dream in blue, remote, untouched, a planet that keeps its secrets beneath swirling methane clouds. But perhaps that's the lesson, that not all mysteries need solving. Some are meant to be felt like wind against a ship's sail, or silence after a long day. Neptune's storms remind us that the universe doesn't always follow logic, that speed can be born in stillness, that the coldest places may carry the fiercest motion. So as you close your eyes tonight, imagine yourself drifting in Neptune's skies, weightless, invisible, carried by a wind that doesn't belong. Let the blue darkness fold around you. Let the impossible be real. And let sleep take you, gently, on the fastest winds that have ever blown. Mercury's icy poles. What if the closest planet to the sun still kept secrets frozen in the dark? Mercury is a world of extremes. Scorched by relentless sunlight, it faces the sun without the buffer of atmosphere or clouds. Its days are oven-hot temperatures soaring above 430 degrees Celsius. Its nights, on the other hand, drop to a bone-cracking minus 180 degrees Celsius. It is a planet of fire and silence, a place that feels too harsh, too close, too burned to imagine anything but dust and heat. And yet, hidden in the shadows of its poles, Mercury holds ice. Yes, ice. In deep, permanent craters near the planet's north and south poles, places where sunlight never reaches water ice has been discovered. The same planet that sits closest to the sun, that has no protective air, no clouds, no shade, somehow cradles frozen water in its darkest corners. How can this be? The answer lies in geometry and shadow. Mercury's axis barely tilts, just 0.034 degrees, so the sun never rises high enough to shine into the deepest craters at the poles. These shadowed regions are eternal night, places where, even as the rest of the planet bakes, the temperature remains cold enough for ice to survive. Not for hours, not for years, but potentially for billions of years. Radar signals bounced from Earth have detected bright reflections from these craters, the unmistakable signature of ice, and NASA's Messenger spacecraft confirmed it with direct measurements. A discovery so strange, it almost reads like contradiction, a frozen secret inside a burning world. But the questions go deeper. Where did the ice come from? Some believe it arrived through comets, ancient icy visitors that slammed into the planet long ago. Others suggest chemical processes may have formed water beneath the surface, slowly releasing vapor that migrated to the poles and froze. Or perhaps it's a mix of both, cosmic delivery, followed by slow preservation in a place that rarely changes. Whatever the source, the presence of ice hints at something fragile and profound, that even in the most hostile environments, small refuges of calm can exist, that even the sun's closest neighbor can harbor cold, clean stillness. And maybe, if ice can exist there, so can other possibilities. Perhaps in ancient times, Mercury had water elsewhere, fleeting streams before they boiled away. Or perhaps someday, we could mine that ice, use it for missions, transform it into fuel, into breath, into life. But beyond utility is beauty. There's something poetic about it that in a world of heat, something quiet and cold still survives. That the universe, chaotic and vast, still carves out pockets of grace. shadows where light cannot reach, secrets that whisper instead of roar. So tonight, imagine standing at the edge of one of those craters. Darkness surrounds you. Above, the stars flicker, the sun a silent fire on the far side. And beneath your feet, ice, pure, ancient, unmoving. A quiet contradiction that reminds you, not everything is what it seems, not everything bright burns, and not everything near the fire has forgotten how to stay cool. Sleep well under Mercury's hidden frost, Earth's wobble in space. What if your home was quietly dancing beneath your feet? We like to think of Earth as solid, steady, reliable, a planet that spins, orbits, and holds us in its gentle gravity. But deep beneath that illusion of stillness, our world is always moving, not just spinning or revolving, but wobbling. This gentle sway is called axial precession, and it means that Earth's axis, the imaginary line running from pole to pole, doesn't point in the same direction forever. Like a spinning top slowing down, our planet tilts and traces a slow, circular pattern through space. A cycle so gradual, it takes about 26,000 years to complete just one full loop. It's almost imperceptible, but its effects ripple through time. Over millennia, it shifts the position of stars in the sky. It changes which constellation the sun appears in during the spring equinox, and it alters our celestial reference points, like the North Star. Thousands of years ago, the guiding star wasn't Polaris, it was Thuban, in the constellation Draco. In another 12,000 years, it will be Vega. This wobble doesn't just change our night sky, it subtly affects climate. It's part of what's known as the Milankovitch cycles, which influence Earth's long-term temperature patterns and may help trigger ice ages. Because as the tilt of the Earth changes, so does the angle of sunlight. Small shifts over vast time adding up to global transformations. But there's more. Earth doesn't just wobble like a top. It also experiences nutation tiny, faster fluctuations caused by the gravitational pull of the moon and the sun. And even more subtle are polar motion and true polar wander, where the entire solid shell of the planet may shift slightly, changing the position of the geographic poles over time. And recently, scientists have found something even stranger. Melting glaciers and redistribution of water due to climate change are altering Earth's mass distribution, slightly shifting the axis itself. Human activity, it seems, is now nudging the planet's balance. A soft fingerprint on a cosmic spin. But all this motion is slow, gentle, like breathing. The Earth wobbles with the patience of stone, a celestial lullaby that plays across eons. So why does it matter? Because it reminds us that even the most familiar things, even the ground beneath our feet, are not fixed. They are part of a deeper rhythm, a dance we rarely feel, but which never stops. And that in every moment, we are slightly different, tilted a little, pointed elsewhere, oriented toward new stars. So tonight, as you lie still, remember, the planet beneath you is swaying, slowly, gracefully, through the galaxy. You are not where you were. And tomorrow, you'll be somewhere new again, not just in time, but in space. Let that movement rock you to sleep. Let Earth's wobble remind you, everything shifts. And that's how balance is born. The soundless vacuum. What if silence was not just the absence of noise, but the nature of the universe itself? Close your eyes and imagine standing in the vastness of space, not aboard a ship, not inside a suit, just you suspended between stars. There's light, yes, distant glows from suns and galaxies. There's movement, two particles racing through the void. But there is no sound, not even a whisper. This isn't silence as we know it. It's something deeper, something absolute. A silence not of waiting, but of nature itself. Because in space, there is no air, no medium, no atmosphere for vibrations to travel through. Sound, which is just pressure waves moving through molecules, cannot exist in a vacuum. You could scream beside a supernova and no one would hear. A planet could shatter like glass, and it would do so in perfect silence. Even when two black holes collide, warping space-time, the sound of it never echoes. Only gravity tells the tale through waves we cannot feel, but can now detect with delicate instruments here on Earth. It's strange, isn't it? That the universe, so full of chaos and creation, plays out its greatest dramas in complete quiet. Explosions that light up galaxies occur in the stillness of perfect hush. Stars are born in silence. Nebulae stretch their luminous arms without a sound. And yet, this silence isn't empty. It's rich. It holds radiation, light, particles, fields, time. It's the backdrop of everything. A quiet stage for all things to appear and disappear. Not absence, but presence without sound. For humans, this concept is unsettling. We live in noise. Our lives are soundtracks of laughter, footsteps, breathing, ticking clocks. Even in the deepest meditation, there's always some rustle, some rhythm. But space offers something more. A reminder that meaning doesn't need volume. That power doesn't always roar. That silence can hold more truth than words ever could. Astronauts speak of this silence with reverence. The way it envelops them, the way it transforms thought. Floating beyond Earth's cradle, they find themselves surrounded by a kind of ancient stillness, not threatening, not cold, but pure, honest. A silence that listens rather than judges. And here's the paradox. While space itself is silent, the universe is full of signals. Radio waves from distant galaxies, pulses from neutron stars, whispers from the Big Bang still echoing across the cosmos. But all of it is invisible to the ear. We translate these signals, we decode them, but we never hear them. Not really. The cosmos sings in silence. So tonight, as you lie in the quiet of your room, let it mirror the void. Let the stillness not feel empty, but eternal. Let it remind you that sound is not needed for significance, that you, like the stars, can exist powerfully and quietly. And may the silence of the vacuum carry you into rest, peaceful, endless, and softly held by a universe that never had to shout. Oumuamua, the visitor from elsewhere. What if something entered our solar system that didn't belong to it? In late 2017, astronomers in Hawaii noticed a strange object moving through the sky. It was fast, too fast, and its path didn't match the usual arcs of asteroids or comets. It wasn't orbiting the sun, it was passing through. A brief guest, a cosmic traveler, a message without a sender. They named it Oumuamua, which means a scout or messenger from afar in Hawaiian. And in many ways, that's exactly what it was. The first known object to visit us from another star system, interstellar. Uninvited, unexplained. But the mystery only deepened from there. Oumuamua wasn't shaped like anything we'd seen, not spherical like an asteroid, not fuzzy like a comet. It was long and thin, possibly 10 times longer than it was wide. Some compared it to a cigar. Others imagined a shard of something shattered long ago. It tumbled through space without spinning regularly. It didn't trail gas or dust, but it accelerated, slightly, as it moved away from the sun. That acceleration puzzled scientists. Objects like comets usually speed up from gas jets ice melting into vapor, pushing the body forward. But Oumuamua had no tail, no visible release, and no clear reason for its motion. Was it a fragment of an ancient planet? A sliver of rock ejected by the gravity of some distant star? A chunk of hydrogen ice? Some speculated it might even be artificial, a probe from another civilization, now silent and drifting, shaped not by nature but design. The truth is, we don't know. Oumuamua came and went quickly, too fast for a mission to intercept, too brief for telescopes to track in detail. By the time the world was asking questions, it was already gone speeding beyond the reach of Earth's instruments into the deep cold between stars. But even in its absence, it left something behind, wonder, a reminder that we are not an island, that the solar system is not a closed system, but a port on the edge of something vaster, that the cosmos still delivers surprises, even after centuries of looking, and perhaps most haunting of all, Oumuamua might not have been the first, just the first we noticed. There could be others. Countless visitors, some long gone, some still to come, moving silently through space, passing close, unseen, remnants of galaxies we've never mapped, debris from civilizations we'll never meet, stories we'll never know how to read. Tonight, imagine standing in a quiet observatory, watching a faint dot trace across the stars, a shape from nowhere, a puzzle with no ending. Let it remind you that the universe does not explain itself. It simply arrives. Sleep under the sky that once welcomed a stranger, and know that somewhere, far from here, Oumuamua still drifts unbound, unclaimed, and utterly mysterious. Planet 9. The ghost in the data. What if a planet was hiding, not behind a shadow, but behind math? Out beyond Neptune, past Pluto's cold orbit, lies the Kuiper Belt, a vast collection of icy rocks, silent worlds, and ancient fragments from the birth of the solar system. It's a quiet place, sparse, dim, but something strange is happening out there. Some of these distant objects, known as trans-Neptunian objects or TNOs, are behaving oddly. Their orbits are elongated, tilted, clustered. It's as if an invisible hand is nudging them from afar, tugging on their paths from the darkness beyond. That hand might belong to Planet 9, a massive, unseen world lurking far beyond Pluto, orbiting the sun in a slow, ghostly ellipse. Not because we've seen it, but because we've seen what shouldn't be happening unless something big is out there, causing it. Astronomers suspect this hidden planet is about 5 to 10 times the mass of Earth, a super-Earth, or mini-Neptune. If real, it would take 10,000 to 20,000 years to complete a single orbit around the sun. So far away, it would reflect almost no light. So distant, it would appear not as a dot, but as a whisper in the data. And the evidence grows. In 2016, scientists Konstantin Batygin and Mike Brown published a study showing how the orbits of 6 peculiar objects couldn't be explained by chance. A pattern was emerging, one best explained by the gravity of an unseen planet. A planet no telescope had yet found. They even suggested where to look. But the sky is vast, and Planet 9, if it exists, might be hiding in a patch of it we haven't scanned closely enough. Or its orbit might be so eccentric that it's currently at its farthest, darkest point, too faint even for our best eyes. Some doubt it exists. Perhaps the data is incomplete. Perhaps the objects were nudged by past stellar flybys, or clumped by self-interactions we don't yet understand. But the tug remains, the anomaly persists, and the search goes on. There's a poetry to this kind of mystery, a planet that may be real, but only mathematically. A ghost whose footsteps we see, even if we cannot yet see the ghost. And if it's real, it would change how we think about our solar system. It would mean our map was incomplete. That one more sibling, large, slow, icy, and far, has been circling with us all along, just beyond reach. It would also mean that the edge is not the end. That even now, in the 21st century, the solar system still holds secrets we've never touched, places where no probe has flown, shadows we've never chased. So tonight, close your eyes and imagine a world you'll never see, a silent planet, wandering far from the warmth of the sun. Invisible, but real. Cold, but present. Like a dream you forgot the moment you woke up. And let that dream lull you into sleep, while Planet 9, if it exists, continues its quiet orbit in the dark. Rogue planets without stars. What if there were worlds that wandered alone? We think of planets as children of stars bound in orbits, warmed by light, tethered by gravity. Earth has the sun, Jupiter has the sun. Even the farthest known planets belong to someone. But scattered across the galaxy are orphaned worlds. Planets without stars, planets that belong to no one. They are called rogue planets, and they drift silently through space, untethered and unseen. No sunrise, no orbit. No warmth except what they carry within. They are the loneliest travelers in the cosmos. How do they come to be? Some may have formed around stars and were later flung away, ejected by violent gravitational interactions with bigger planets, or disturbed by passing stars. Others might have formed on their own, in the cold clouds of dust that never became stars. Either way, they now move through the galaxy in solitude, invisible in the darkness, and yet there may be many. Astronomers estimate that for every star in the Milky Way, there could be 2 to 3 rogue planets. That's billions of planets, floating, wandering, without light, without orbit. A hidden population of cold black marbles moving silently through the interstellar void. We've found hints of them using gravitational microlensing, a technique that watches how their gravity bends the light from background stars as they pass by. It's subtle, a flicker, a blink, a distortion lasting just hours or days. Enough to know something passed, but not enough to see it directly. Some of these rogue planets may be massive, the size of Jupiter or bigger. Others may be small, rocky, Earth-sized. And here's the wonder. Some of them might still have heat. Their cores could be warm, their surfaces covered in thick atmospheres or frozen oceans. A few scientists even speculate that life's strange, dark, silent life could exist there. Not dependent on sunlight, but on geothermal energy, chemical reactions, or hidden subsurface seas. A planet alone is not necessarily a planet dead. Imagine it, a world with no sky, no day, no stars, just an eternal night beneath thick clouds or ice. Winds moving without direction, oceans kept liquid by inner heat, entire biospheres sealed from the universe, never knowing light, never needing it. It's haunting and beautiful. That the galaxy could be full of worlds we'll never see. Not because they're too far, but because they don't shine. They don't reflect. They don't wait to be found. And yet they move, quietly, like forgotten thoughts in the mind of the cosmos. So tonight, as you close your eyes, think of them, these silent travelers. Let their solitude soften your own. Let their drifting reassure you. Because even in the vast dark, you are never the only one who wanders. Sleep under the stars and remember that not every world needs one. Triton's backward dance. What if a moon moved the wrong way and no one could stop it? Far out in the frozen realm of Neptune spins a moon unlike any other. Its name is Triton, and it dances to a rhythm that defies the norm. Most moons orbit their planets in the same direction the planet spins, but Triton does the opposite. It orbits backward in what scientists call a retrograde orbit. This isn't just a curiosity. It's a profound mystery, a cosmic clue that something strange happened long ago. Triton is massive, almost as big as Earth's moon, and too large and too strange to have simply formed beside Neptune. Its backward motion suggests it wasn't born there. Instead, most believe Triton is a captured object, once a dwarf planet, perhaps like Pluto, roaming the Kuiper Belt. At some point in the deep past, it passed too close to Neptune and got caught, trapped by gravity, claimed not by birth, but by force. That capture would have been violent. Any previous moons Neptune had might have been torn apart or flung away to make room. And Triton itself, once free, became bound, forced into a backwards loop. And now it spins there still, locked in Neptune's grip, pulled slowly inward with each passing century. Yes, Triton is falling, not quickly, not dramatically. But with time, it spirals ever closer to Neptune. Eventually, millions or billions of years from now, it may crash into the planet or be torn apart by tidal forces, forming a ring. A moon that becomes dust. A backward story that ends in silence. But before that happens, Triton continues to astonish. Despite the cold around -235 degrees Celsius, Triton has geysers. Dark streaks on its surface suggest it spews nitrogen gas from beneath its icy crust, possibly from heat generated by internal friction or decay. It's one of the few places in the solar system with active ice volcanism where frozen landscapes still move, still breathe. Its surface is young, smooth in many places, with strange terrains and few craters. This means it's being reshaped even now. A moon that defies not just gravity, but age. And all the while, it dances backward, against Neptune's spin, against the expected order, like a memory moving in reverse, like a traveler refusing to forget where it came from. There's something deeply poetic about it, a captured wanderer, now a rebel moon, slowly drawing closer to the planet that stole it, like a satellite caught in an unwilling embrace, unable to escape, unable to rest. So tonight, imagine looking up from Triton's surface. Neptune would fill the sky blue, vast, ever turning while you move in the opposite direction. Let that reversal soothe you. Let it remind you that not all who resist the flow are lost. Some are just remembering who they were. Sleep well. As Triton continues its backward ballet, one quiet orbit at a time. Pluto's heartbeat. What if a frozen world still pulsed with life? Pluto, once the 9th planet, now reclassified as a dwarf, orbits at the distant edges of our solar system. It is small, icy, remote. And yet, in 2015, when NASA's New Horizons spacecraft flew past it for the first time, we saw something we never expected, a glowing heart, a vast, bright region shaped like a valentine. One side smooth, the other textured. This is Tomball Regio, named after Clyde Tombaugh, the man who discovered Pluto in 1930. But many simply call it Pluto's heart. It's not just a poetic image. That heart-shaped plane tells a deeper story. It reveals motion, change, a kind of quiet defiance against the idea that Pluto is dead. The western lobe of the heart is known as Sputnik Planitia, a basin filled with nitrogen ice, roughly the size of Texas. Its surface is smooth, almost eerily so, with no impact craters. That means it's young, geologically fresh. Something has erased the past. Something is renewing it. This plane pulses. Warmed slightly from below by Pluto's interior heat, the nitrogen ice may convect rising and sinking in slow motion currents like a frozen lava lamp. These cycles may take hundreds of thousands of years, but they are real. They keep the heart smooth, beating in a way across cosmic time. No one expected this. Pluto, so small and far from the sun, was supposed to be inert, but instead we find evidence of glaciers, mountains made of water ice, possibly even cryovolcanoes where liquid slush erupts instead of fire. The planet's surface is young in places and old in others. It is layered, active, alive in its own frozen language. Some even speculate that deep beneath Pluto's crust, there could be a subsurface ocean. Trapped under ice, warmed by radioactive decay, it might persist to this day, silent, undisturbed. A sea beneath a heart beneath a world. If true, that changes everything. It means even the coldest bodies in the solar system might hold liquid water, might hold the potential for life, not in sunlight, but in shadow, not in heat, but in hidden warmth. And all of this mystery, this motion, this improbable rhythm is visible in a single image. A heart etched into the ice of a forgotten world, facing the stars. So tonight, let that image hold you. A planet demoted and distant that turned out to be full of beauty. A surface that remembers, reshapes, renews, a heartbeat that no one expected. Sleep in the quiet glow of that distant heart. Let it remind you, even the smallest, most overlooked things can carry the deepest mysteries. And sometimes, love really is written into the surface. Asteroids with moonlets. What if even the smallest things had companions? When we imagine moons, we think of large planets, Jupiter with dozens, Saturn with rings and satellites, Earth with one glowing friend in the sky. But out in the asteroid belt and far beyond, something quieter happens. Asteroids, tiny rocky remnants drifting through space, sometimes have their own moons too. Not giant, shimmering ones, but little companions, often called moonlets. These are not poetic orbits crafted by cosmic design. They're rough, irregular, unpredictable, yet they exist a rock, pulling another rock into its gravity, forming a tiny dance in the darkness. One of the first discoveries was 243 Ida, an asteroid visited by the Galileo spacecraft in 1993. To everyone's surprise, it had a moon later named Dactyl. Just a few kilometers wide, it orbited its parent like a faithful shadow. That single image, an asteroid and its moon, changed how we understood these leftover fragments from the solar system's formation. Since then, astronomers have found many more. Some binary, where two asteroids orbit each other. Others with small satellites trailing along. These aren't rare flukes. It turns out, about 15% of near-Earth asteroids larger than 200 meters have a moonlet. They're more common than we thought, just harder to see. How do they form? Sometimes, from collisions, a bigger asteroid gets hit, sending debris into orbit that later coalesces. Other times, a fast-spinning asteroid might fling off a piece of itself through a process called rotational fission. Over time, gravity takes over, and the fragment settles into orbit. Fragile, shifting, but real. And while these systems are small, they are rich with clues. By studying their orbits, scientists can learn the mass and density of asteroids' insights into what they're made of, how they formed, and how they might behave if one ever threatened Earth. Some even imagine future missions to these tiny double worlds. One day, we might land on both members of a binary asteroid system, study their shared center of gravity, float between them like a cosmic tightrope walker, or even use their low-gravity environments for mining, or as way stations deeper into space. But there's a softer beauty in this too, that even a lump of rock drifting silently through the void might not be alone. That even in the coldest, emptiest parts of space, things can still hold each other. Imagine two objects, dark, silent, irregular, spinning around one another, locked in a slow, patient orbit. No light, no life, just mass and gravity and time. And still, they stay connected. Tonight, as you fall asleep, picture them, asteroids with moons, lonely travelers with quiet company. Let that image remind you that companionship doesn't need warmth or language. Sometimes it's just presence, just staying near, just not letting go. Because even a rock can cast a shadow, and even a moonlit can belong. Comets that disappear. What if some visitors left no trace behind? Comets are the wanderers of the solar system, frozen time capsules from its earliest days. They emerge from distant reservoirs like the Kuiper Belt or the Oort cloud, arcing toward the sun with long, glowing tails made not of fire, but of ice and dust pushed by solar wind. They arrive, brighten, pass, and retreat into darkness. But not all of them follow the script. Some comets, after journeying into view, simply vanish. They dim, they break apart, they fade without warning. Astronomers track them across the sky, predicting their paths, awaiting their return, only to find silence, nothing where something should be. These are the disappearing comets, ghosts in the solar system. And their mystery lies not in where they go, but in why they go nowhere. One famous case is Comet Elenin, discovered in 2010. As it approached the inner solar system, conspiracy theories bloomed wild claims about doomsday, secret planets, cosmic alignments. But before any of those fantasies could be addressed, the comet broke apart. Solar radiation and tidal forces unraveled it into dust. By the time it reached closest approach to Earth, it was gone, dissolved. A headline without a comet. Other comets have vanished without drama, just slow, steady disintegration. Some lose too much mass near the sun. Others collide with unseen debris or get torn apart by Jupiter's gravity. A few may even be false comets, asteroids misclassified due to unusual brightness or behavior. What we think is ice becomes stone. What we expect to shine does not. Sometimes a comet disappears only to reappear years later changed, smaller, dimmer, a fragment of its former self. Other times it is truly lost. Its name remains in records, but no orbit can be followed. A path erased. To the ancient world, comets were omens, flashing beacons of fate. But to modern science, they are windows into the birth of planets, the chemistry of water, even the building blocks of life. Their disappearance isn't failure. It's part of their story, a reminder that not everything is meant to last. And perhaps that's what makes them beautiful. A comet is fleeting by design. It comes close, shines briefly, and recedes. And when it disappears entirely, it leaves us not just curious but moved, because not all vanishings are losses. Some are just completions. So tonight, picture a comet tail trailing behind it, sunlit and spinning, carving an arc through space. And then, gone, dissolved into invisible dust, like a thought you forgot or a dream you didn't write down. Let that softness lull you. Let it remind you that brilliance doesn't always end with applause. Sometimes it ends with stillness. And in that quiet, something remains. The orbit of Sedna. What if something circled the sun from almost beyond the sun's reach? In 2003, astronomers discovered a small, distant world orbiting far beyond Pluto. They named it Sedna, after the Inuit goddess of the sea, a fitting name for a planet-like object lost in the cold deep of space. But Sedna is no ordinary object. Its orbit is one of the most mysterious in the solar system, so long, so stretched, so detached, that it seems to belong not just to another region, but almost to another system. It takes more than 11,000 years for Sedna to complete just one orbit around the sun. Let that sink in. A full Sedna year is longer than all of human history. Its orbit is elongated, with a closest approach still beyond the Kuiper Belt and a farthest point that disappears into interstellar space. It does not come near any known planet. It's as if Sedna is obeying a different gravity, a hidden tug, a ghostly whisper from something unseen. Some scientists believe Sedna's bizarre path hints at the presence of Planet 9, the massive, invisible planet we spoke of earlier, whose gravity might be shepherding objects like Sedna into their strange trajectories. Others suggest that long ago, a passing star in the early days of the solar system disturbed the outer disk, flinging Sedna into a path that remains warped to this day. There's even a wilder idea, that Sedna and others like it may have come from another solar system altogether. That it's an interstellar immigrant, adopted into our sun's family during a close stellar encounter in the galaxy's youth. A visitor who stayed. But what Sedna truly represents is the beginning of the inner Oort cloud, a theoretical zone beyond the Kuiper belt where icy bodies drift in slow, distant orbits untouched by light or time. These are the solar system's outermost messengers, forgotten relics. Waiting. We don't know what Sedna is made of exactly. Its surface is red, the deepest color of any known solar system body, suggesting complex organic compounds, tholins, created by cosmic radiation over eons. It reflects little sunlight. It shines, dimly, only to those who know where to look, and for most of its orbit, Sedna is unobservable, too far, too faint. It visits the inner part of the solar system only once every 10 millennia. That means every sighting of Sedna, every photograph, every data point is a glimpse into a moment that will not return for thousands of generations. A visitor passing through, slowly, silently, without fanfare. So tonight, imagine a world you'll never stand on, orbiting a Sunday you'll never see from that far away. Let it remind you of how wide our home truly is. That even now, we have neighbors drifting in the dark, on timelines that laugh at our calendars. Sedna moves, not quickly, but faithfully, a red ember in the edge of everything. Let its long orbit cradle your thoughts. And rest, knowing some mysteries are not meant to be solved, only witnessed, briefly, before they pass beyond the light again. Strange tilts of Uranus. What if a planet rolled through the solar system on its side? Uranus is often the quiet one, distant, dim, pale blue. It orbits in the frozen outskirts of the solar system, whispering its secrets through the chill. But look closer, and you'll find one of the most bizarre mysteries of all the planets. Uranus is tilted almost completely sideways. Most planets spin upright or with a gentle lean. Earth, for instance, tilts at 23.5 degrees, just enough to give us seasons. But Uranus? It's tilted 98 degrees. It doesn't just lean, it lies down. It spins like a ball rolling on its edge. Its poles, rather than its equator, face the sun. That means for nearly half its 84-year orbit, one pole is bathed in constant sunlight while the other sits in shadow. A day on Uranus can last 42 years of sunlight, followed by 42 years of night. Why? The leading theory is violence. Long ago, in the solar system's chaotic youth, Uranus may have collided with a massive object, a young planet, or perhaps several large impacts over time. These crashes could have knocked it over, reshaping its axis and tipping its spin into this strange orientation. A giant that was struck and never stood upright again. But this tilt has effects beyond just awkward seasons. Uranus has rings like Saturn, but faint and narrow. And because of the tilt, those rings orbit vertically, almost like the brim of a spinning top. Its magnetic field is also twisted, not centered, not aligned, but chaotic and lopsided, wobbling as the planet turns. Even its moons orbit in strange ways, caught in the same tilted rhythm, circling a planet that never quite faces forward. All of it, the rings, the spin, the field, the moons, points to something deeply broken, or perhaps deeply unique. A planet that doesn't follow the rules, that spins not with the solar system, but across it. And yet, Uranus remains stable. Its rotation is steady. Its orbit is faithful. It may be tilted, but it is not lost. It rolls through the dark with quiet dignity, never correcting itself, never pretending to be something it's not. There's something tender in that you can be tilted and still move forward, that you can be knocked over and still orbit the sun. So tonight, imagine drifting above Uranus, watching it turn slowly on its side serene, blue, cold. Let its quiet resistance ease your thoughts. Let its tilted grace remind you that stability doesn't always look symmetrical, and sleep knowing that even the most off-balance souls still belong in the solar dance. The sun's galactic drift. What if even the sun was just passing through? We think of the sun as the center, the still point, the anchor that holds the solar system together. And in a way, it is. Planets orbit it. Moons follow the planets. Asteroids and comets trace spirals through its gravitational pull. But the sun itself is not standing still. It's moving, always. Our entire solar system, planets, moons, dust, ice, you and me, is riding a star that's flying through the Milky Way at 828,000 kilometers per hour. Faster than anything we can see. And yet, we never feel it. Because the drift is constant, smooth, silent. It takes the sun about 225 to 250 million years to complete one full orbit around the galaxy center. That means the last time our solar system was in this same spot in the galaxy, dinosaurs hadn't yet existed. It means Earth has circled the galactic core maybe 20 times since it was born. This slow, patient drift is called the galactic orbit, and it's not a perfect circle. It wobbles, it sways. Our solar system bobs above and below the galactic plane like a leaf in a stream. Some scientists believe these oscillations might even affect life on Earth, nudging us through regions of dense star fields, triggering cosmic events, maybe even influencing cycles of extinction. It's only a hypothesis, but the idea is haunting. We are not just spinning on a planet. We are not just orbiting a star. We are sailing through a galaxy, and the galaxy too is drifting, pulled by gravity, toward other galaxies, toward the great attractor, toward a future we cannot see, carried on motions we cannot stop. Sometimes we look up at the stars and think they are fixed, but they are not. They move, slowly, like lanterns on an unseen tide. The constellations we know are temporary. A few thousand years from now, Orion's belt will stretch. The Big Dipper will bend. Our star map will wrinkle and change. Even Polaris, the North Star, is just the current North Star. In a few thousand years, another star will take its place. Because Earth wobbles, the sun drifts, the galaxy spins, and everything changes. Yet in that motion, there is peace. The sun does not resist the drift. It simply flows. It pulls us gently along a river of stars, never hurrying, never pausing, just moving as it always has, as it always will. So tonight, as you lie still, remember this: stillness is relative. You are hurtling through the galaxy, and yet you feel calm, safe, anchored. Let the drift comfort you. Let it rock you. Let it remind you that motion doesn't need direction to be meaningful. You are not lost. You are part of the drift. Sleep well, traveler of the galactic tide. Gravitational lensing, seeing through gravity. What if gravity could bend light like glass? In the silence of space, light travels in straight lines, or so we once believed. For centuries, we pictured it like an arrow shot across the cosmos, direct, unwavering, pure. But in 1915, Einstein proposed something different. In his theory of general relativity, gravity was not a force, but a curvature. Mass bends spacetime, and spacetime tells light how to move. And that means light doesn't always travel straight, it curves. This bending of light around massive objects is called gravitational lensing, and it is one of the most elegant, eerie phenomena in the universe. It turns galaxies into magnifying glasses. It lets us see what lies behind things we could never reach. It's not magic. It's gravity, sculpting sight. Imagine this: a galaxy far, far away emits light in all directions. But between it and us, there is another massive object, a closer galaxy, a cluster, maybe even dark matter. That mass warps the fabric of space around it, like a bowling ball on a trampoline. As the light passes through, it bends, wrapping around the gravity well, distorting and focusing like a lens. The result? We see the background galaxy magnified, stretched, sometimes split into arcs or even full rings of light. These are called Einstein rings, and they are breathtaking. Glowing circles in the sky, formed not by design, but by alignment of mass, distance, and time. Sometimes, lensing creates multiple images of the same object, copies of a galaxy or quasar, scattered like a cosmic mirage. Other times, it brightens the faint, revealing things too distant to see directly. In fact, much of what we know about the early universe, the first galaxies, the first stars, comes from gravitational lensing. But lensing doesn't just show us what's there, it also shows us what's not. Because we can measure how light is bent even when we don't see what's doing the bending. That's how we discovered dark matter, the invisible mass that outweighs everything we can see. We know it's there, not because we detect it, but because it pulls on light. Because it leaves fingerprints in the way the stars distort. Gravity becomes a sculptor, light, its medium, and the universe, a gallery of distorted beauty. So tonight, imagine the sky as a lens, not flat, but rippled. Not silent, but whispering in curves. Let go of the idea that straight is the only way forward. Let gravity pull your dreams in gentle arcs. Because even light, the fastest thing we know, is humbled by mass. And in that humility, we see farther than ever before. Sleep beneath a sky that bends, and let the hidden shapes of the cosmos unfold behind your closed eyes. Redshift and the expanding sky. What if distance made everything red? When you hear the word redshift, it sounds like something dramatic, and in a way, it is. It's the whisper of the cosmos as it drifts apart, the stretching of light, the slowing echo of stars long gone. And behind it lies one of the strangest truths of the universe. Everything is moving away. When a light source moves away from you, its waves stretch out like a siren, sounding lower as it passes. In sound, this is called the Doppler effect. In light, the same thing happens. The waves stretch, the frequency drops, and the light shifts toward the red end of the spectrum. Red light is lower in energy, longer in wavelength, and it is the signature of cosmic escape. The farther away a galaxy is, the more its light is redshifted. Not because it's just moving through space, but because space itself is expanding. This discovery was not expected. In the early 20th century, Edwin Hubble observed that distant galaxies were all redshifted and not randomly, but in proportion to their distance. The farther they were, the faster they appeared to be retreating. The universe was not static, it was growing. Imagine this. Space itself is a rubber sheet. Galaxies sit like coins on that sheet. As the sheet stretches, the coins move apart, not because they're sliding, but because the space between them is expanding. That's what redshift tells us. The light from distant galaxies gets stretched as the fabric of reality grows beneath it. This stretching turns visible light into infrared, into microwaves, even into radio waves. The cosmic microwave background, the oldest light we can detect, is just redshifted radiation from the Big Bang, cooled and stretched over 13.8 billion years. So when we look at redshifted light, we're not just looking far, we're looking back in time. Galaxies as they were, light as it once glowed, a sky that no longer exists in the form we see, and it's not slowing down. In fact, the expansion is accelerating. Galaxies are fleeing faster over time, driven by something we call dark energy, a mysterious force that pulls everything apart. The more space there is, the more expansion occurs. And one day, if it continues, even nearby galaxies may disappear from view. Their light stretched beyond detectability, a future sky with fewer stars. But there's something beautiful in this too, that the universe is not frozen, that it breathes, expands, flows, that every photon carries with it the fingerprint of movement. That color itself is a kind of history. So tonight, let your mind drift into the red. Let your thoughts stretch like light across a growing sky. Let go of the idea of stillness. The universe is a wave, and you are riding it. Sleep while galaxies slide quietly away, and let the redshift sing you to rest. Quasars, beacons from the edge. What if the brightest lights came from the darkest places? Far across the universe, beyond the reach of most telescopes, something ancient flickers. Brighter than entire galaxies, they shine with a light that has traveled billions of years to reach us. These are quasars, the most luminous, most powerful objects ever observed. But their brilliance hides a paradox, because at their center is darkness. Quasars are not stars, they are not galaxies. They are the glowing cores of distant galaxies, where a supermassive black hole is actively devouring matter. As gas and dust spiral into the black hole's event horizon, they heat up not to a flicker, not to a flame, but to a radiant inferno. The friction, gravity, and magnetic chaos generate energy so intense that it outshines every star in the surrounding galaxy. And from Earth, we see that glow not as a gentle light, but as a blinding signal from the edge of time. The name quasar comes from quasi-stellar radio source, because when first discovered in the 1960s, they looked like stars in photographs, but emitted strange radio waves. Their redshifts were enormous. It meant they were incredibly far away, and yet, somehow, impossibly, blazingly bright, brighter than a trillion suns. How can something that far still be seen? Because it is ancient light. Quasars were most active billions of years ago when the universe was young and chaotic. Galaxies collided, black holes fed. The cosmos roared with new formation, and quasars lit the darkness like beacons in a deep ocean, marking the violent birth of structure. Today, most quasars have faded. The black holes are still there quiet, dormant, but the fuel is gone, the fire has dimmed. What we see now is their past, their youth, their brightest scream frozen in time. a fossil of light drifting toward us across space. And that's what makes them so haunting. When you observe a quasar, you are not seeing something as it is. You are seeing something as it was billions of years ago. A flare from a black hole that has since grown silent. A light that left its home before Earth had oceans, before trees, before thought. Some quasars have jets, narrow beams of energy shooting out from their poles at near light speed, powered by magnetic fields and rotation. These jets span thousands of light years. They pierce through space like cosmic needles, mapping lines no hand could ever draw. And yet, they are silent. No sound, no echo, just light, just memory. Just a slow, inevitable decay of brilliance into history. So tonight, close your eyes and picture a quasar, a dark heart wrapped in furious light, spinning, devouring, glowing, a lighthouse in the void. Let it remind you that even darkness can radiate, that even destruction can create beauty, and that sometimes what looks like a star is something far stranger and far older. Sleep under the light that began before we began, and dream of fires that have long since gone out, still warming the sky. Gamma ray bursts, cosmic flashbulbs. What if the universe blinked? In the vast silence of space, most events are slow. Stars take millions of years to die. Galaxies drift like clouds across centuries. But every so often, without warning, the sky flashes. A brief, blinding burst of energy. A blink and it's gone. These are gamma ray bursts, or GRBs, the most powerful explosions in the universe. Invisible to the eye, but bright enough in gamma wavelengths to outshine everything else in the cosmos for a few seconds, and then nothing. Discovered by accident during the Cold War, GRBs were first detected by satellites designed to catch nuclear detonations. Instead, they found flashes coming from space. Random, short, confusing. Scientists had no idea what they were. For years, they were just anomalies, ghosts in the data. Now, we understand a little more. There are two kinds. Long-duration GRBs lasting more than 2 seconds are thought to be the final cries of massive stars collapsing. When a star many times larger than our Sunday exhausts its fuel, its core implodes, forming a black hole. As matter spirals in, jets of energy shoot out from the poles, unleashing beams of gamma rays that travel across the universe. Short-duration GRBs, under 2 seconds, are stranger still. They likely come from collisions when two neutron stars smash together in a cosmic dance of gravity and destruction. These mergers produce not just gamma rays, but ripples in space-time gravitational waves which we can now detect. In both cases, what we see is not the event itself, but a fleeting shadow of it, a flash, a fingerprint of violence so far away, it takes billions of years to arrive. And when it does, it is already over. A single GRB can release more energy in 10 seconds than our Sunday will in its entire 10 billion year life. Let that sink in. More than a lifetime of light in the blink of an eye. And yet, GRBs are focused directional. Unless Earth happens to be in the path of the beam, we wouldn't even know they happened. Countless bursts may go unnoticed, aimed at nowhere we can see. Others we catch by luck, a brief flare, then silence. If one ever occurred nearby, it could be catastrophic, but most come from the edges of the universe, far enough that they do not threaten, only whisper. They are not stars. They are stories of endings, of things collapsing so completely they can only be understood through the energy they leave behind. So tonight, imagine that blink, a silent flash of unimaginable power, light that raced toward you before humanity ever existed, arriving now in this moment, not to destroy, but to remind you how small you are, how vast it all is, how quiet violence can be. Let the darkness fold around you, and sleep, knowing the universe has blinked and you are still here in the quiet after. Time dilation near black holes. What if time didn't move the same for everyone? We often treat time like a constant, a ticking clock, a metronome of existence. Seconds pass, minutes add up, hours flow. But near a black hole, that rhythm breaks. Time itself begins to stretch, to slow, to bend under the weight of gravity. This is not science fiction, this is relativity. According to Einstein's theory, massive objects warp the fabric of space-time. The greater the gravity, the more severe the curvature, and the slower time flows. Nowhere is this more extreme than near a black hole. Black holes are collapsed stars. their mass packed into an infinitely dense point. Their gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, the point of no return. But before you even reach that horizon, something stranger happens. Time itself begins to dilate. If you were to hover just outside the edge of a black hole, seconds would stretch into minutes, minutes into hours. To you, everything would feel normal. But to an outside observer far from the black hole's pull, you would appear to be moving in slow motion. They would watch you age more slowly, move more slowly, speak more slowly. Time, for you, would flow gently. This phenomenon isn't just theory. We've seen its effects near neutron stars, near massive planets, and even on GPS satellites, which must correct for time differences caused by Earth's own gravitational field. But around black holes, the effect becomes profound, almost poetic. In a way, black holes are time machines for the future. Fall close enough and the universe outside accelerates. Galaxies spin faster. Stars are born and die in moments. A day for you might be centuries out there, but you can never go back. Only forward, only deeper into the dark. And yet, in that darkness, time is not lost. It's preserved, dilated, cradled in gravity's embrace. The movie Interstellar played with this idea. A planet near a massive black hole, where 1 hour equaled 7 years on Earth. A fictional world, yes, but grounded in real physics. And perhaps, one day, we'll test it for ourselves. Because time, we're learning, is not just a backdrop. It's a dimension, a substance that bends, warps, responds to gravity like silk in water, and black holes are the deepest wells in that sea. So tonight, let go of the ticking clock. Let yourself float near the edge of the event horizon. Let your breath slow, your thoughts stretch, your heartbeat become still. You are not late. You are not early. You are exactly where time wants you to be. And somewhere, out there, a black hole waits where a single moment can last forever. The twin paradox. What if the moment you said goodbye was the last time you aged the same? Imagine two identical twins, born together, growing up side by side. Then, one boards a spaceship and leaves Earth at near the speed of light. The other stays behind. Years pass. For the twin on Earth, it's a normal life. But for the one in space, time is moving differently. When they reunite, something astonishing happens. The spacefaring twin has barely aged. The Earthbound twin is old. This is the twin paradox, one of the strangest, most haunting predictions of Einstein's theory of special relativity. And it's not just a thought experiment. It's a real, measurable effect, one that changes how we understand time, motion, and what it means to age. Here's how it works. At speeds close to the speed of light, time slows down for the traveler compared to someone who stays still. This isn't a trick of perception. It's physical. Clocks on board the spaceship tick more slowly. Heartbeats slow. Cellular processes stretch. The twin on the ship lives fewer seconds, even though to them, everything feels normal. Meanwhile, back on Earth, time flows at its usual pace. Decades pass, generations change, history unfolds, and when the spaceship returns, the two timelines meet again, no longer synchronized. It feels like magic, but it's not. It's the geometry of space-time. Time and space are linked, one bends, the other flexes. And when you move through space quickly, you move through time slowly. What makes it a paradox is the symmetry. Each twin sees the other as moving. So why doesn't each age less? The resolution lies in acceleration. The traveling twin turns around, decelerates, and returns, breaking the symmetry. They change frames of reference. And with that change comes the cost, a shorter personal timeline. This isn't just theory. We've tested it with atomic clocks flown on airplanes. With particles moving near light speed in colliders, each time relativity proves true. And so, the twin paradox becomes more than physics. It becomes a quiet fable, a story about leaving and returning, about the cost of motion, about how even shared beginnings can lead to profoundly different ends. It asks you, if you could travel fast enough to touch the stars, but return to find everyone you loved aged beyond recognition, would you still go? Would the journey be worth the silence? So tonight, imagine standing at a launch pad, your twin beside you. You wave goodbye, not knowing how much older they'll be when you return. And as you drift into sleep, feel time stretch and slow your own personal relativity. Let go of the ticking clock. You are not late. You are not behind. You are just moving. And sometimes that's enough. Light that travels billions of years. What if the light you see left its source before Earth even existed? Every night, we look up and see stars, some twinkling close, some faint and far. But what you're really seeing is the past. Because light, though unimaginably fast, is not instant. It takes time to travel, and across the vast distances of space, it can take billions of years to arrive. That means the stars above you are not as they are, but as they were. The Andromeda Galaxy? Its light takes over 2 million years to reach Earth. You're seeing it as it was when early humans were still learning to walk upright. A quasar at the edge of the observable universe? That light began its journey more than 13 billion years ago, before Earth was born, before the sun ignited, before even galaxies had settled into their spiral shapes. The photons that hit your eye tonight have crossed time itself. They've passed through expanding space, dodged galaxies, dark matter, and dust, stretched and cooled, changed color. They've outlived stars, drifted through silence, and arrived, now, right now, into you. This is one of the quietest miracles in all of science, that by simply opening your eyes, you're catching messages from a cosmos that has already moved on, reading echoes, seeing fossils, catching the flickers of things long gone. Some of that light may come from stars that no longer exist, that exploded, collapsed, dimmed, but their light, their story is still arriving, still traveling, still telling you that they were once there. In this way, space becomes a kind of memory. A glowing scrapbook of what was, a film reel playing backwards. We do not see the universe as it is, but as it was. And the farther we look, the further back we go. Astronomers use powerful telescopes as time machines. They stare deeper and deeper into the abyss, not to predict the future, but to reconstruct the past. To watch the universe assemble itself, one photon at a time. Every image a snapshot, delayed. Every galaxy, a ghost. And the universe itself? It may be infinite, but the observable part is not. The farthest light we can ever see is limited by the age of the cosmos, about 13.8 billion years. Anything farther is invisible. Not because it isn't there, but because its light hasn't arrived yet. Or never will. So tonight, as your room dims and your thoughts slow, picture the light entering your window. Not from the lamp or the phone, but from stars. From ancient suns. From forgotten explosions at the edge of time. Let it remind you, even light needs time. Even stars have stories. And even now, you are part of that journey. Close your eyes and let the oldest light in the universe drift gently through your dreams. The photon sphere. What if light could be trapped in orbit? We usually think of light as free. It moves fast, straight, unbound. Nothing, after all, travels faster than light. It races from stars, reflects off planets, and reaches our eyes without effort. But near a black hole, the rules change. In that strange gravity, even light can be caught. There is a place just beyond the event horizon where photons don't escape and don't fall in. Instead, they orbit. This boundary is called the photon sphere. It's a delicate zone. Not inside the black hole, but not far enough to flee its pull. If a beam of light enters it at just the right angle, it will begin to loop, not in a spiral, not in a bounce, but in a perfect, endless orbit, trapped by the curvature of space-time. Imagine a ring of light, spinning around darkness. A halo with no origin, no end. The photon sphere lies at 1.5 times the Schwarzschild radius, the mathematical surface of the black hole, also known as the event horizon. Any closer, and light falls inward. Any farther, and it curves away. But right there, balanced on a razor's edge of gravity, it dances. It's not stable. In reality, photons in this sphere don't stay forever. A small nudge, a shift, a disturbance, and they fall in, or escape. But, for a moment, they orbit. Light turned into a satellite. This concept isn't just theoretical. It helps shape one of the most iconic scientific images ever, the first photograph of a black hole's shadow. What we saw in that image, the bright ring surrounding the darkness, was caused in part by photons circling the black hole, some for multiple orbits before escaping toward us. A photon echo, a glimpse of light caught in gravity's embrace. The photon sphere also leads to strange optical effects. If you could somehow hover near it and look out, you'd see the back of your own headlight from behind you bent full circle. The sky would wrap, stars would twist, up would fold into down. It's a place where direction becomes meaningless, where forward means circling, where light, the fastest traveler in the universe, becomes a captive. But there's something quietly poetic in this, that even light, the great liberator of shadow, can be held, not broken, just delayed, just curved. So tonight, close your eyes and imagine a ribbon of light, orbiting something it can never touch, never leave. Let its loop lull you. Let its silence wrap around your thoughts like a glowing ring. You are not falling. You are not escaping. You are circling gently around the unknowable. Sleep within the photon sphere, where light learns patience. The unreachable present. What if now was always just out of reach? We often talk about the present moment as if it's something solid, immediate, the slice of time we're actually living in. But in the vast geometry of space-time, the now isn't so simple. In fact, it may not even exist the same way for everyone or anyone. This is the strange truth of relativity. Simultaneity is an illusion. Events that seem to happen at the same time from one perspective may not be simultaneous to someone else, moving at a different speed or in a different gravitational field. The faster you move, the more your concept of now shifts. On Earth, we barely notice, but across light years, across galaxies, the idea of a shared present starts to unravel. There is no universal clock ticking for all. What you consider now on a distant star may already be someone else's past or someone else's future. Even if we could observe it instantly, relativity says time is relative. Motion distorts it. Gravity bends it. The present slips. Light, too, delays us. When you look at the moon, you see it as it was 1.3 seconds ago. The sun, over 8 minutes ago. The nearest star system, more than 4 years ago. The deeper you gaze, the farther back in time you go. You have never seen the present. Not even your own reflection is truly now. The light bouncing from the mirror to your eye takes time. Infinitesimal, yes, but still a delay, still a gap. And yet, we live as if now is real. We act, we speak, we love. We believe the moment exists not because physics confirms it, but because our minds insist on it. Our brains are wired for continuity, for coherence. They stitch together sensory delays and processing time into a seamless flow. The world seems immediate, but in reality, we're always catching up, always interpreting, always a beat behind. The present is not a point, it's a zone, a blur, a mental construction layered on top of physical delay. What we call now is just the overlap of what we remember, what we sense, and what we expect. A flickering illusion held steady by habit, and somehow, it works. Somehow, even without access to the true present, we live full, vibrant lives. We plan, we reminisce, we dream, we build meaning not on precision, but on participation. So tonight, as you close your eyes, feel the gentle weight of time brushing past. Not sharp, not fixed, but soft, flowing. Let go of the need to be exactly now. Let yourself drift a few seconds behind the stars, because the present may be unreachable, but in its place is something even better, presence. Sleep in the comfort of a moment you'll never catch, and know that it's still enough. Starlight that outlives stars. What if the light you see was the last breath of something already gone? Stars are born, live, and die across spans of time that dwarf our own. Some live for billions of years, others burn bright and fast, collapsing in just a few million. But even when a star dies, even when it explodes or fades into darkness, its light continues on. That's the strange, gentle truth of the cosmos. Light outlives its source. When a star sends its photons out into space, those photons don't stop when the star goes dark. They keep traveling, silently, tirelessly, across the void. They move through galaxies, past clouds of dust, beyond the pull of planets, until one day they arrive. Maybe in the lens of a telescope, maybe in your eye, maybe in a moment like this. And when you see that light, you are witnessing something that no longer exists. Not as it was. Not in the same form, not in the same place. You are seeing echoes. You are watching the ghosts of stars. Some of the most distant galaxies we photographed existed billions of years ago. Their stars have since died. Their shapes have changed. Some may not exist at all anymore, swallowed by collisions, shredded by time. But their light is still here, crossing oceans of silence to meet us. Even stars in our own galaxy obey this rule. The star Betelgeuse, in the shoulder of Orion, is nearing the end of its life. It could go supernova at any moment. Or perhaps it already has. And we're just waiting for the news, waiting for its final flash to arrive, centuries after the event. In this way, space is a library of past lives. The night sky is not a live broadcast, it's a delayed message written in photons. It tells us what the universe used to be, what it tried to become, what it remembers. There's something comforting in that even after something ends, it can still be seen, still be felt, still light the darkness for someone else. We too leave traces, words, touch, kindness. Our presence, like starlight, can ripple long after we're gone. What we say tonight may reach someone years from now. What we build, what we love, what we share, it travels. It remains. So tonight, as you fall asleep, let the sky be your memory. Lie beneath the glow of stars that no longer burn. Let them remind you that endings are not erasures. That light has a life of its own, that you too are made of echoes. Sleep knowing this. Even when the fire fades, the glow continues. The Great Wall of Galaxies. What if the universe built walls no hand could touch? When we think of a wall, we picture something solid, physical, meant to divide or contain. But in the cosmos, walls are not made of bricks or stone, they're made of galaxies. Thousands upon thousands of them, arranged not randomly, but in vast, intricate structures that span billions of light years. One of the most astonishing of these is simply called the Great Wall. Discovered in 1989, the Great Wall is a massive cosmic filament, a sheet of galaxies stretching over 500 million light-years across. It's not a straight line. It's more like a curtain, a lacework of clustered galaxies bound together by gravity and arranged across the cosmos like veins in a leaf. But it's just one piece of something larger. As our observations deepened, we found more. The Sloan Great Wall, even bigger. The Hercules Corona Borealis Great Wall, possibly the largest structure ever detected, so vast that it challenges our understanding of the cosmic principle, the idea that the universe is roughly uniform in all directions. These structures aren't walls in the traditional sense. They are boundaries of emptiness. They form the edges of enormous cosmic voids, regions where few galaxies exist. Imagine a foam of soap bubbles, where the walls are dense with galaxies and the bubbles themselves are vast gaps. That's the large-scale structure of the universe. Not scattered, not random, but woven. The galaxies in these walls are bound together over unimaginable distances by dark matter, the invisible scaffolding that gives structure to space. Without it, there would be no galaxies, no clusters, no walls. Just dust. And we're inside this pattern too. Our own Milky Way lives in a filament called the Laniakea Supercluster, a name meaning immeasurable heaven. It's our local neighborhood, made of galaxies flowing toward a gravitational basin called the Great Attractor. We are part of this web, not separate from it, but suspended in its threads. What causes these walls to form? Gravity, time, ancient quantum ripples stretched by inflation in the early universe. Like waves frozen in place, the echoes of the Big Bang shaped where matter clumped and where it fled. Over billions of years, these ripples became structure. And now we see them not as chaos, but as cosmic architecture. So tonight, as you lie still beneath your ceiling, picture a wall not of wood or stone, but of galaxies glowing like lanterns. Imagine walking beside it each step taking 1,000,000 years. Imagine looking up and seeing not one star, but a tapestry of galaxies, endless and shimmering. And know this, you are not alone on a rock in a void. You are part of a filament, part of a wall, part of a structure that holds the shape of everything. Sleep softly, wrapped in the patterns of the universe. The Sloan Great Attractor. What if everything around you was being pulled towards something you can't see? In the vast ocean of galaxies, there's a quiet motion, a drift, a draw. Not of a single planet or a single star, but of entire clusters of galaxies, all flowing in the same general direction. It's not random, it's not a mistake, they're being pulled. And the force behind that pull is something astronomers call the Great Attractor, a mysterious gravitational anomaly located hundreds of millions of light years away, in the direction of the constellation Centaurus. We don't know exactly what it is. We only know that we, the Milky Way, the local group, the Virgo supercluster, and countless other galaxies are moving toward it, not just slowly, but at around 600 kilometers per second. That's over 2 million kilometers per hour. The Great Attractor isn't a single object. It's not a black hole or a star or a galaxy. It appears to be a region of space densely packed with galaxies and dark matter so massive that it bends the motion of everything nearby. But much of it lies in a part of the sky blocked by our own galaxy's dust and stars. We call it the zone of avoidance. Even our best telescopes struggle to see through that veil. And so, much of what we know comes from indirect measurements observing how galaxies move, how their redshifts skew, how their positions lean in one shared direction. It's like watching boats drift toward a current you can't see. In time, the Sloan Digital Sky Survey and other deep scans revealed even more structure in that region, layered walls, filaments, and clusters beyond clusters. Names like the Norma Cluster, the Shapley Supercluster, and the Sloan Great Wall began to form a picture, a gravitational ballet, choreographed by something massive, hidden, and patient. The Great Attractor may not be a final destination. We may simply be passing through its pull on our way to something even larger. The Shapley concentration, a titanic supercluster farther still. What matters is this: everything is in motion, even the things we think of as fixed. Our galaxy, our solar system, our own planet, all caught in a current that flows towards something we've never seen. A drift not caused by explosions or momentum, but by gravity itself, quiet, relentless, invisible. And what's perhaps most poetic, you can't feel it. This cosmic movement doesn't stir your body. It doesn't bend your bones, but it's happening all the time. You are being pulled, gently, persistently, by a structure you will never touch, toward a mystery no one can fully name. So tonight, close your eyes, and let yourself feel the softness of that pull. Let it carry your thoughts outward. Let it remind you that everything is moving, even you, even now. The universe doesn't need your awareness to work, but it offers you the gift of knowing you're part of its motion. Sleep in the arms of unseen gravity. Dark flow. What if the universe had a hidden current? Everything we see in the cosmos moves. Galaxies expand away from one another. Stars orbit, planets spin. But in 2008, scientists discovered something strange, something beyond expansion, beyond gravity, beyond what we expected. They found a drift. A quiet, unaccounted for motion of galaxy clusters, all moving in the same direction toward a specific patch of sky, beyond the known cosmic structures. A smooth, coherent flow stretching over hundreds of millions of light years. They called it dark flow. This was more than just expansion. The universe itself is growing, yes, but that growth should be mostly uniform. Galaxies should fly apart in all directions. But in the data from the Wilkinson Microwave Anisotropy Probe, WMAP, a peculiar pattern appeared. Distant galaxy clusters seemed to be streaming, as if tugged by an invisible hand, toward something. But what? That's the mystery. No known structures should exist far enough or massive enough to cause this. The pull doesn't fit into our map of the observable universe. It seems to come from outside it, beyond the horizon of what light has had time to reach us. A region we cannot see. A place we cannot know. Some suggest a massive accumulation of dark matter or a distant supervoid. Others whisper about even stranger things, the influence of a parallel universe, or leftover imprints from the multiverse. The idea that our cosmos might be just one of many, and their gravity, their presence, still presses against ours. But there is no proof, only drift, only motion. Only this eerie, consistent direction, like all of space, is leaning gently toward a place that isn't there. The data was controversial. Later missions, like Planck, didn't confirm it as strongly. The evidence dimmed, the certainty blurred. But still, the idea lingers that the universe may be tugged by something it cannot explain. There's something quietly beautiful about that. The thought that we might be part of a current we can't see. That everything, stars, galaxies, atoms, thoughts, may be caught in a flow from some unreachable elsewhere, not pulled by gravity we can measure, but by presence, by mass or meaning outside of time. And maybe that's not so different from life. We drift, too pulled by forces we don't always understand, by longing, by memory, by dreams we haven't seen but somehow feel. We move toward things without knowing why. So tonight, allow yourself to drift. Let go of maps, of plans, of precision. Let your breath be a galaxy. Let your thoughts dissolve into the current. And sleep while the universe, quietly and mysteriously, flows around you. Filaments of the cosmic web. What if the universe was woven? From Earth, the night sky looks like a sea of scattered stars, isolated, twinkling points adrift in blackness. But when we zoom out, far out, the randomness dissolves. Something begins to take shape. A pattern, a structure. We call it the cosmic web, the large-scale skeleton of the universe. A vast, three-dimensional lace of filaments stretching across billions of light years. These filaments are not made of thread or dust, but of galaxies, superclusters, rivers of stars, and between them, voids. Enormous, empty pockets of space where almost nothing exists. The web is not smooth, it's not even, but it's connected, woven like veins across the face of everything. Each filament is a highway of matter, formed by gravity over billions of years. After the Big Bang, the universe was almost uniform, a warm mist of particles. But tiny fluctuations, seeded by quantum mechanics, grew larger over time. Gravity pulled more and more material into dense regions, forming strands, nodes, clusters. The rest emptied out. And from those strands, galaxies were born. Our Milky Way isn't floating alone, it's suspended inside a filament, part of a larger supercluster known as Laniakea. The galaxies around us aren't scattered, they're aligned, drawn together by a shared, invisible blueprint shaped by dark matter and time. Simulations show it clearly. Pour enough particles into a virtual universe, let gravity do its work, and the web appears. Not just once, but always. It's the universe's natural form. Not chaos, but geometry. Even more haunting, these filaments aren't just beautiful. They may be alive in motion. Galaxies aren't static. They flow along these threads, migrating slowly over cosmic time, drawn toward denser nodes, massive intersections where clusters gather and evolve. We've mapped some of these filaments using surveys like Sloan and DESI, but most remain invisible, hidden in the dark matter scaffolding that gives them shape, like bones beneath the flesh of the sky. And here's the softest part. We may be connected to galaxies we've never seen, not just by physics, but by structure. The same filaments that cradle us, cradle them, across light years, across eras. We are held, not alone, not random, just part of a web that hums quietly across the dark. So tonight, as you lay still, imagine yourself nestled in one of those filaments, a glowing point on a glowing string, stretching into forever. Let it hold you like a thread in a great design. Let it remind you that even in the vastness, even in the quiet, connection is real, and sleep gently woven into the fabric of it all. The baryon mystery. What if half of everything was simply missing? In the language of the cosmos, matter as we know it, the stuff we're made of is called baryonic matter. It includes protons, neutrons, atoms, molecules, stars, gas, planets, people. It's the visible universe, tangible, measurable, familiar. And yet, for decades, scientists were haunted by a quiet, unsettling question. Where is the rest of it? When they tallied up all the matter visible in galaxies, stars, clouds, and clusters, and compared it to predictions from the early universe, something didn't add up. About half of the baryons were missing. Not dark matter, not dark energy, just ordinary matter gone. This became known as the baryon missing mass problem. The numbers from the cosmic microwave background, the echo of the Big Bang, told us how much matter there should be. And yet, when we looked at the nearby universe, we only found half of it. Where did it go? The answer, it seems, is not that it vanished, but that it hid. In 2017, scientists using X-ray telescopes and radio observations found strong evidence that much of the missing baryonic matter exists in the form of WIM, the warm-hot intergalactic medium, not stars, not galaxies, but vast filaments of diffuse, heated gas stretched thin between galaxies, glowing faintly at millions of degrees. These filaments thread the cosmic web, forming bridges between clusters. But they're hard to detect and visible in most light, too spread out to shine, too faint to catch without the right tools. Only by looking for absorption lines against background quasars like fingerprints on cosmic light could we trace their presence. What we discovered is quietly stunning. The universe has always been full. We just didn't know how to see it. The missing half wasn't lost. It was floating between galaxies, sleeping in filaments, glowing too softly to notice. And in a way, that's deeply human. We often miss what's there, not because it's gone, but because we weren't looking in the right way, or with the right eyes. The baryon mystery teaches us something gentle. That absence is not always a void. Sometimes, it's just a whisper. So tonight, imagine those filaments, rivers of invisible gas, stretching between galaxies like cosmic breath. Picture them glowing faintly, pulsing with heat, not gone, just quiet. Let that silence settle in your thoughts. Let it remind you that not all things that matter are visible. And sleep knowing this, even what seems missing may only be waiting to be found. The zone of avoidance. What if the universe hid right behind your own galaxy? We've mapped the cosmos in every direction. We've traced galaxies across billions of light years, built charts of filaments, voids, clusters. We see further than ever before. And yet, there's a blind spot. A region of the sky where our vision dims. A gap in the grand map. Astronomers call it the zone of avoidance. It's not empty. It's not mysterious in the way black holes or dark matter are. It's simply obscured. The zone of avoidance lies behind the thick disk of the Milky Way, hidden by stars, gas, dust, and glowing clouds that block our view of what lies beyond. When you look up at the dense band of the Milky Way, you're seeing the very thing that blinds us. The galaxy's bright core and swirling arms scatter light, absorb signals, and create a curtain that hides distant galaxies beyond it. Roughly 20% of the sky veiled. Imagine trying to see a city skyline through a dense forest at night. You might catch a flicker, a glow, a shadow, but never the whole view. And yet, what lies behind that curtain could be profound. Some of the universe's most massive structures, including the Great Attractor and the Shapley supercluster, lie in or near this zone. Their gravity affects the motion of entire clusters. We know they're there because we feel their pull galaxies drifting toward them, space flowing in their direction. But we don't see them directly. Not fully, not clearly. For decades, the zone of avoidance lived up to its name. But now, using infrared, radio, and X-ray telescopes, astronomers are beginning to peer through the dust. These wavelengths pass through the haze, revealing the faint signatures of hidden galaxies long concealed. We're slowly filling in the gaps one data point at a time, but the idea still lingers, that even in our most complete maps, there are blind spots. Even in our greatest clarity, there are places we cannot reach, and perhaps that's okay. Because the zone of avoidance is not just a region of space, it's a reminder that some truths are always half hidden, that even with the best tools, we're still learning how to see, and that sometimes the thing hiding the answer is also part of the answer. So tonight, close your eyes and picture the Milky Way as both a bridge and a veil, a galaxy that nurtures us and gently blocks our view. Let it remind you that mystery doesn't always live in darkness. Sometimes it lives in light that's too bright, too close, too familiar. Let that comfort you. Sleep, knowing the universe still holds places we haven't reached, not because they don't exist, but because we're not finished looking. And that's what makes the sky so quietly infinite. The cold spot in the CMB. What if the afterglow of creation had a bruise? Long ago, nearly 14 billion years, the universe was young, hot, and glowing. That light, stretched and cooled over time, became the cosmic microwave background, the faint echo of the Big Bang. It fills the universe like a soft, ancient hum, uniform, gentle, but not perfect. Scattered across this cosmic backdrop are tiny fluctuations, temperature differences just a few millionths of a degree apart. These ripples are normal, expected. They gave birth to galaxies, stars, and structure. But one ripple is different. It's called the cold spot. Located in the constellation Eridanus, the cold spot is colder and larger than theory predicts. It's not just a small dip, it spans over 1,000 light years across, and it's cooler by about 70 microkelvin. Tiny in temperature, vast in size, a quiet contradiction at the heart of our best model. We expected noise, but this looks more like a scar. At first, scientists wondered if it was an error, a glitch in the data. But multiple instruments from the Wilkinson Microwave Anisotropy Probe, WMAP, to the Planck satellite confirmed it. The cold spot is real, and it won't go away. So what caused it? One idea is the Sachs-Wolf effect, where light from the early universe loses energy while climbing out of a massive gravity well. But for the cold spot to be explained this way, the void causing it would have to be impossibly large, larger than anything we've seen. Another theory suggests it's the imprint of a supervoid, a massive, empty region of space between us and the cold spot, sapping energy from the photons that pass through. This would cool the light, like wind stealing heat from your skin. But even this explanation feels stretched. The void would need to be enormous, and we've only found weak evidence of one that size. And then, there's the possibility that the cold spot is something else entirely. A bubble from a different universe. A collision between realities. A wrinkle in the multiverse. A place where our universe brushed against another in its early inflation, leaving a smudge, a memory, a chill. No one knows. It may be a statistical fluke, and unlikely, but natural deviation in the great random quilt of the early cosmos. Or it may be something deeper, a secret stitched into the sky. Whatever it is, it remains. Cold, quiet, patient. So tonight, imagine the sky as a canvas, painted by time, and imagine one patch cooler, darker, slightly out of place, a whisper of something other. A gentle reminder that even the earliest light we can see holds questions we still can't answer. Let the cold spot cradle your sleep. Let its mystery be your lullaby. Because sometimes, the most peaceful places are the ones we do not fully understand. The Sachs-Wolf anomaly. What if gravity could chill the light of creation? The cosmic microwave background, or CMB, is the oldest light we can see, a soft glow from the dawn of time, when the universe cooled enough for atoms to form and photons to travel freely. It wraps around us in every direction, a baby picture of the cosmos itself. But that light didn't travel through emptiness. It crossed billions of years of structured galaxies, clusters, voids, gravity wells, and in doing so, it changed, slightly, subtly, enough to tell a new story. This shift is known as the Sachs-Wolf effect. Discovered by Rainer Sachs and Arthur Wolf in 1967, the effect describes how gravitational potential alters the temperature of photons from the early universe. As light climbs out of a dense gravitational well, say, a massive galaxy cluster, it loses energy, appearing cooler. If it falls into a gravity well on its way toward us, it gains energy, appearing warmer. It's like light trying to hike uphill. Most of these shifts are small and expected. They paint the texture of the CMB, those tiny variations in warmth and cold that seeded all cosmic structure. But then comes the anomaly. The integrated Sachs-Wolf effect, a twist on the original, predicts that as the universe expands and accelerates due to dark energy, large gravitational wells can change during a photon's journey. If the well flattens or stretches while light is passing through, the photon doesn't regain all the energy it lost climbing out. The result? A net cooling, a smudge on the cosmic canvas. We've detected signs of this. We see temperature correlations between the CMB and the distribution of galaxies, as if light was softened by the large-scale structure of the cosmos. But some anomalies go further than expected, deeper, stranger. Like the cold spot, this effect hints that something isn't perfectly uniform. And here's where the mystery deepens. Some regions of the sky show Sachs-Wolf fluctuations larger than they should be. Some appear asymmetrical, challenging the assumption that the universe is homogeneous on large scales. It's as if something shifted in the very fabric of expansion. Not enough to rewrite our models, but enough to whisper that we might be missing something. A ripple in the pattern, a deeper pull, a broken symmetry in the earliest light. Is it an error, a coincidence, a sign of unknown physics? No one can say for sure. But the Sachs-Wolf anomaly remains quiet, mathematical, chilling. A reminder that even our best maps of the beginning carry questions we cannot answer. So tonight, close your eyes. Let the early universe fold around you, light climbing in and out of invisible hills. Photons cooled by time, bent by gravity, stretched across expanding space. A journey of 13 billion years to reach you now. Sleep, knowing the cosmos still speaks. Not loudly, not clearly, but with shifts so soft, only silence can hear them. Cosmic isotropy or not? What if the universe had a preferred direction? One of the quiet assumptions in cosmology, simple, elegant, foundational, is called cosmic isotropy. It means the universe looks the same in every direction. No matter where you point your telescope, the laws of physics hold. The sky, on a grand scale, is uniform. It's a comforting thought. But what if it's not quite true? The idea of isotropy goes hand in hand with homogeneity, the belief that the universe has no center, no edge, no privileged perspective. It forms the backbone of general relativity, of the Big Bang Theory, of how we model everything. But in recent years, cracks have begun to show. Not loud, not definitive, just soft nudges, gentle, unsettling deviations. Some studies of the cosmic microwave background suggest a subtle alignment, a axis of evil. As some cheekily call it, a strange pattern in the CMB's low multipole moments that doesn't sit well with perfect randomness. The temperature fluctuations, instead of scattering uniformly, appear to point in a common direction. That shouldn't happen. Other observations deepen the mystery. Quasar polarizations in deep space seem aligned over billions of light years, as if these ancient galaxies, scattered across time, were somehow influenced by the same cosmic compass. Even the motion of our own galaxy through the universe, the so-called dipole anisotropy, adds to the puzzle. Some astronomers have looked into hemispherical asymmetry, finding that the northern half of the sky might have slightly different properties than the southern half. Tiny differences in expansion rates, in density, in structure. Again, nothing loud, but enough to wonder. Could the universe be slightly lopsided? Could it have inherited a kind of directional memory from the Big Bang, an ancient wrinkle in its initial conditions? Or are we seeing patterns where none exist, cosmic pareidolia born of incomplete data? There's no clear answer, and maybe that's what makes it beautiful. Because if the universe really is anisotropic even a little, then we must rewrite our deepest assumptions about symmetry, about origins, about what it means to observe. And if it's not, then the mystery becomes a lesson in humility, a reminder that even the cleanest theories must face the messy, unpredictable world. So tonight, lie back and let the sky fold around you. Point your thoughts in every direction, north, south, inward, outward. Let them stretch like galaxies in expansion. Let them drift without needing a destination. And remember, maybe the universe is perfectly even. Maybe it has a subtle tilt. Either way, you are part of its pattern, and your direction, tonight, is toward rest. The universe's fractal question. What if the universe repeated itself, no matter how far you zoomed in? A fractal is a shape that looks the same at every scale. Zoom in, and the pattern remains. Zoom out, and it returns again. From snowflakes to ferns, coastlines to lightning bolts, nature loves this rhythm, a kind of visual echo. But what if the universe itself followed the same rule? This is the fractal universe hypothesis, the idea that the cosmos may not be smooth and homogeneous at large scales, as we've long believed, but instead self-similar, structured, layered, repeating. The standard model of cosmology says that once you reach a scale of about 300 million light-years, things even out. Galaxies, clusters, filaments, they blend into a uniform soup. That's what our models assume. Beyond a certain point, the universe becomes statistically smooth, but some observations have challenged this. In the 1990s and early 2000s, galaxy surveys including the Sloan Digital Sky Survey revealed structures far larger than expected. Giant walls of galaxies, enormous voids, sheets and filaments extending over hundreds of millions of light years. They didn't look random, they looked recursive, like veins branching out in patterns that repeat. Some researchers propose that maybe, just maybe, the cosmos doesn't smooth out. Maybe it continues to show fractal-like structure at even larger scales. A universe not of randomness, but of infinite texture-layered complexity as far as we can see. Of course, this remains controversial. Most cosmologists still believe in large-scale homogeneity. Fractal patterns appear, yes, but only up to a point. Beyond that, the universe calms down. But the question still lingers. What if scale is an illusion? What if the tiniest grain of space echoes the shape of the whole? What if galaxies and atoms whisper the same song, the rhythm of repetition? It wouldn't be the first time nature surprised us. We see recursion in tree branches, in blood vessels, in clouds. Perhaps the universe simply followed the same blueprint, and maybe so do we. Our thoughts, our memories, our choices layered like a fractal mind, repeating stories in different scales. Childhood moments echoed in adult fears, dreams recurring in different forms. Everything looping and returning, like patterns in a great design. So tonight, imagine yourself as part of that pattern, a single spiral in an infinite dance, no beginning, no end, just layers unfolding, like galaxies woven into galaxies, thoughts into dreams. Let the question rest in your chest like a quiet drumbeat, and sleep, knowing that even if the universe does not repeat, you do, in love, in memory, in the stardust that made you, the gaping void. What if the universe had a silent hole? In a cosmos filled with stars, galaxies, gas, and light, you might expect that emptiness would be rare. That space, even when quiet, is never truly alone. But then we found a void. A place so vast, so empty, it bends belief. It's called the Eridanus supervoid, a dark patch of the sky, stretching over 1 billion light years across, with far fewer galaxies than expected. Not entirely empty, but eerily underpopulated. Like walking into a city where all the buildings are gone and only the roads remain. This isn't just a hole in the map. It's a cosmic anomaly. Its most unsettling feature? It sits directly behind the cold spot in the cosmic microwave background. That strange cooler region in the afterglow of the Big Bang. A coincidence? Maybe. Or maybe not. Some scientists believe this void could explain the cold spot. As photons from the early universe pass through such an enormous emptiness, they lose energy redshifted by the stretched out structure of space-time. This could account for the chill we observe in that patch of the sky. But there's a problem. The void would have to be enormous, larger, and deeper than any other we've seen. Big enough to question our models, big enough to break expectations. And even then, the cooling effect might still be too small to match the cold spot fully. Which raises a deeper question. Why does such a vast emptiness exist at all? Galaxies tend to clump together, drawn by gravity into filaments and clusters. Between them, voids form naturally. But nothing quite like this. Not this size, not this alignment, not this silence. Some theorists go further, suggesting the void might be more than an accident, that it's the result of primordial quantum fluctuations, early wrinkles in the inflation of the universe. Or perhaps something more exotic. A scar from another universe, a cosmic wound where two realms collided and left behind a fingerprint. We don't know, but it lingers. A hole in the sky that swallows light, blurs predictions, and dares us to explain its quiet. And yet, even this silence teaches us something soft. That absence can carry meaning. That emptiness is not the opposite of presence, but a presence of its own. So tonight, let your thoughts drift across that cosmic hollow. Float above its darkness, its peace, its scale. Imagine what it means for something so vast to hold so little and yet to mean so much. Let the gaping void be your reminder that sometimes, in stillness, we feel the most. Quantum fluctuations in space-time, what if even emptiness was never truly empty? At the smallest scale imaginable, beneath atoms, beneath quarks, beneath the fabric of what we call real lies, a realm of flickering uncertainty. A place where energy pops in and out of existence like fireflies in a dark field, where silence itself is alive. These are quantum fluctuations. Even in a perfect vacuum, no particles, no light, no heat, the rules of quantum mechanics say the energy is never zero. It pulses, it seethes. Particles appear and disappear in pairs, like dancers dipping into and out of existence. This is not theory, it's been measured. The Casimir effect, for example, demonstrates that two metal plates placed very close together in a vacuum will attract each other. Not because of any force we see, but because of the pressure from these invisible fluctuations all around them. The vacuum breathes. Now, stretch this idea to the cosmos. In the early universe, tiny quantum fluctuations, minute differences in energy, no larger than an atom were stretched to galactic scales during cosmic inflation. They became the seeds of everything: galaxies, stars, planets, even us. These flickers of nothing became everything. But here's where the mystery deepens. What if these fluctuations still shape space-time itself? Some theories suggest that space-time is not smooth, but grainy, pixelated. At the Planck scale, the smallest scale with physical meaning, reality may jitter and foam like the surface of a stormy sea. Tiny fluctuations cause microcurvatures in space, even in what appears to be emptiness. This is called quantum foam, a hypothetical structure where time and space fluctuate, warp, and twist unpredictably at scales far too small to observe. We don't know what it looks like, but it may explain things we cannot yet grasp: dark energy, the origin of mass, even the emergence of time itself. It's like the entire universe is floating on a quantum sea, calm on the surface, but roiling underneath. And maybe, at the deepest level, the universe isn't built on certainty, but on possibility. Not on being, but becoming. Because a fluctuation is a maybe, a could be, a whisper of potential waiting to collapse into form. So tonight, imagine yourself resting on that ocean of uncertainty. Feel the quiet beneath your thoughts, the hum behind the stars, the truth that even in stillness, something stirs. Sleep, knowing that the universe began with a tremble in the void, and in every moment, in every breath, in every dream that tremble continues. The arrow of time, what if time only flows forward, because we believe it does? We experience time like a river always moving, never reversing. The past feels fixed, the future uncertain, and the present a fleeting moment we can never hold. This flow feels natural, obvious, absolute, but physics disagrees. Most of the fundamental laws from Newton's to Einstein's to quantum mechanics work the same forward and backward. If you filmed a single atom in motion and played it in reverse, the math wouldn't mind. Time, in equations, has no preferred direction. So where then does the arrow of time come from? The answer may lie in something quiet, something hidden: entropy. Entropy is the measure of disorder in a system. And according to the second law of thermodynamics, entropy always increases in a closed system. Things fall apart, ice melts, ashes don't become firewood again. And this, perhaps, is the only law that truly gives time a direction. From low entropy to high, from order to chaos. Our universe began in an astonishingly low entropy state, smooth, simple, calm. And ever since, it has been unraveling, growing more complex, more disordered, more fragmented with every tick of the cosmic clock. This unfolding gives us memory, cause and effect, the feeling that time is moving. But here's the mystery. Why did the universe start that way? Why, out of all possible beginnings, did it start in such unlikely order? Some suggest it's a fluke, a 1 in a trillion coincidence. Others think deeper that entropy is tied to cosmic inflation, or that time itself may be emergent, not fundamental. That what we perceive as time is just the echo of deeper processes we don't yet understand. Even more strangely, some physicists propose that before the Big Bang, time may have flowed backward, that the arrow of time could flip under certain conditions, that in other universes or even deep inside black holes, time might not flow like ours at all. And if that's true, then maybe time is not a river, maybe it's a tide, rising and falling, shifting direction, looping back. Maybe it's not about clocks, but change. Not about minutes, but memory. So tonight, rest your mind on the gentle stream of now. Let go of the past, it's a pattern you no longer need to carry. Let go of the future, it hasn't unfolded yet. Stay in this breath, this quiet moment, and know that time, whatever it truly is, will wait for you here. Time reversal in black holes. What if falling into a black hole meant falling backward through time? Black holes are strange enough already. They bend space, trap light, swallow stars whole. But deep inside, past the event horizon, lies something even more mysterious than gravity. Something that bends not just space, but time. Let's start where everything ends, the singularity. In the heart of a black hole, gravity becomes infinite. Matter collapses to a point of zero volume, and our equations fall apart. Space-time warps so severely that the familiar rules no longer apply. But here's the twist. Inside a black hole, time and space swap roles. Outside, we move through space freely, and time flows forward. Inside, it's the opposite. Time becomes the direction you fall. You cannot stop, cannot hover, cannot escape, because falling inward is no longer just motion through space. It's motion through time. And that time points toward the singularity. There's no going back. But what does that really mean? It means that, from the perspective of someone falling in, the singularity isn't just a place, it's a moment in the future, inevitable, like tomorrow. And just as you can't jump from Wednesday back to Monday, you can't escape the pool once you've crossed that threshold. But then, things get weirder. Some theoretical models suggest that if a black hole connects to a white hole, its hypothetical opposite time might reverse. A white hole expels matter instead of pulling it in. It cannot be entered, only escaped. Like time running backward, undoing collapse, ejecting memory. In certain solutions to Einstein's equations, like the maximally extended Schwarzschild solution, this pair forms a kind of tunnel, a wormhole, linking two regions of spacetime, one collapsing into a singularity, the other uncollapsing from it. Time flowing in reverse. No one knows if white holes are real, or if wormholes can truly exist. But the math allows for the possibility that deep within black holes, the arrow of time bends backward. That what looks like an end from one side is a beginning from the other. And if time can reverse in such places, what does that say about reality? What does it say about endings? What does it say about death? Maybe the laws of physics don't end at the singularity. Maybe they just rearrange. What seems like finality may be transformation. What seems like collapse may be rebirth. So tonight, close your eyes and let your thoughts fall inward. Fall past gravity, past light, past understanding. Let time stretch and bend around you. And imagine that even the darkest place in the cosmos might still carry the seed of another dawn. Gravitational time dilation. What if time ticks slower at the bottom of a well? It sounds like fantasy, like something out of science fiction, but it's real, measurable, and it happens every second of your life. It's called gravitational time dilation. According to Einstein's theory of general relativity, time isn't fixed. It's woven into the fabric of space-time, and that fabric can stretch, bend, or warp depending on mass. The more mass, the stronger the gravity. And the stronger the gravity, the slower time moves. If you stand at the top of a mountain, time moves slightly faster than it does at sea level. If you live on the ground floor of a skyscraper, your clock runs more slowly than your neighbors on the 80th floor by an almost imperceptible fraction of a second. But zoom out, and this becomes profound. Near a black hole where gravity is immense, time practically stops. Imagine an astronaut hovering near the edge of a black hole, the event horizon just outside the point of no return. To her, everything feels normal. Time flows as it always does. But to someone watching from far away, her clock ticks more slowly. Her heartbeat, her breath, her entire life stretches out. If she hovered long enough, she could witness centuries pass in the blink of her eye. A minute to her, a millennium to us. This is not science fiction. This is how time behaves under gravity. We've even tested it. In 2010, scientists placed ultra-precise atomic clocks, just 1 foot apart, one slightly higher than the other. And they tick differently. Height alone changed the passage of time. Gravity's subtle influence bending not just space, but rhythm. It raises strange questions. What is time, if it can stretch? What is aging, if it depends on position? And what becomes of memory in a universe where time is elastic? Some physicists have speculated that time dilation near black holes might allow a kind of time travel one-way trips to the future by riding the slow lane of gravity. Others dream of ships parked near neutron stars, where decades pass outside while moments pass within. But the truth is quieter. Gravitational time dilation shows us that time is not absolute. It's not the same for everyone, everywhere. It flows differently depending on where and how deeply you stand in the universe. And maybe that's a metaphor too, because just like gravity shapes time, our experiences shape how we feel it. Some days rush, others crawl. Moments near loss or love stretch longer than hours ever could. Emotion becomes gravity, and time bends with meaning. So tonight, feel the weight of your own presence. Let gravity hold you gently. Let time pass more slowly here, in this stillness, where nothing demands you move. And know, wherever you are, time is flowing just for you. Frame dragging and twisted space-time. What if space itself could be twisted like syrup? We often think of space as a passive stage, a blank canvas on which stars move, planets orbit, and galaxies collide. But Einstein taught us it's not a stage, it's a fabric, a living thing. And under certain conditions, it twists. This phenomenon is called frame dragging. Imagine stirring a spoon in honey. The honey swirls around the spoon, dragged along by its motion. In a similar way, a massive rotating object like a spinning planet or a black hole drags the very fabric of space-time around with it. It's not just theory, it's been measured. In 2004, NASA's Gravity Probe B confirmed this prediction. 4 gyroscopes were placed in orbit around Earth, floating in near-perfect isolation. According to Newton, they should have pointed in the same direction forever, but they didn't. They drifted, ever so slightly, because Earth slowly spinning was twisting space-time around it. Now imagine something more massive, a neutron star, a Kerr black hole. These objects spin at unbelievable speeds and their frame dragging is far more extreme. Near a spinning black hole, space-time isn't just warped, it's whipped into a swirl. This region is called the ergosphere, the outer layer of a spinning black hole where nothing can remain still. Even light is forced to rotate. You can still escape the ergosphere, unlike the event horizon, but you can't avoid being dragged. Everything is caught in the cosmic whirl. And here's the strangest part. In theory, you could extract energy from this twist. It's called the Penrose process. A particle enters the ergosphere and splits in two. One half falls into the black hole. The other escapes and steals some of the black hole's rotational energy with it. Just by leveraging the spin of space, it's a wild idea. But it's real physics. Frame dragging teaches us something humbling. Even empty space is not still. It reacts, it moves, it swirls in the presence of mass and motion. Which means the universe is not only stretching, it's spinning. And maybe so are we, because we too are shaped by forces we don't always see. Emotional gravity, momentum from the past, the spin of memory, the inertia of stories we were born into. Sometimes we feel dragged by history, by identity, by motion we didn't choose. But knowing this can also free us. We can use that motion, lean into the twist, redirect the flow. Just like a photon riding the edge of a spinning black hole, we can find new direction inside the swirl. So tonight, let the world spin gently beneath you. Let space bend and turn. And sleep knowing that even the deepest twists of the universe might carry you forward. The great attractor. What if something was pulling us across the universe and we didn't know what it was? Our galaxy, the Milky Way, is not standing still. Neither are its neighbors. Together, they form a cluster called the local group, and it's drifting not randomly, but purposefully towards something massive, something hidden, something we call the Great Attractor. It lies in the direction of the constellation Norma, some 250 million light-years away, and though we can't see it directly obscured by the thick dust of the zone of avoidance, where our own galaxy blocks the view, its presence is undeniable. Because we feel its pull, our galaxy is moving at over 600 kilometers per second, not just from expansion, but from attraction. Something massive lies in that darkness, tugging at hundreds of thousands of galaxies, guiding them like leaves caught in a current, and yet, we don't know exactly what it is. At first, scientists thought the Great Attractor might be a massive cluster of galaxies, and indeed, the Norma cluster, with its dense web of galaxies, resides in that region. But as our instruments improved and our maps of the universe grew, we discovered something bigger still. Beyond the Great Attractor is the Shapley supercluster, a gravitational colossus, even more massive, even more distant. And suddenly, the Great Attractor looked less like the destination and more like a waypoint, a stepping stone on a much longer, much stranger journey. So now astronomers wonder, are we being pulled not to one point, but across a vast gravitational landscape towards something we can't yet comprehend? And if so, what does that mean? What is gravity showing us that light cannot? Perhaps this is a reminder that motion is not always guided by what's visible, that sometimes the most powerful forces are felt not seen. We are moving even when we don't know why. We are drawn forward even when the source of our momentum is hidden. Like emotions we haven't named, like memories we've forgotten but still feel. We are shaped by distant centers of gravity, some real, some imagined. Maybe the Great Attractor is not a place, but a metaphor. For the unseen forces in your life pulling you forward. For the truths just outside your awareness, calling you through intuition, through longing. Tonight, let go of needing to see everything clearly. Rest in the mystery. Let the pull of the unknown carry you, softly, through the stars. And no, even if you don't know the destination, you are moving towards something vast. The dark flow. What if the universe was being pulled by something outside itself? It begins with a drift, subtle, persistent, unsettling. Astronomers studying galaxy clusters noticed something strange. These massive structures weren't just moving randomly. They were all headed in the same direction, across vast regions of space. Not because of local gravity, not because of known forces. Something was pulling them, something deep, something dark. They called it the dark flow. It's not part of the universe's expansion, the stretching of space-time that pushes galaxies apart. This motion is different. It's not outward, but directional. A silent tug guiding galaxy clusters at hundreds of kilometers per second toward a mysterious region of the sky, near the constellations Centaurus and Vela. But here's the problem. That region lies beyond the observable universe, outside the range of light, past the cosmic horizon, the edge of what we can see, limited by the speed of light and the age of the universe. In theory, nothing on the other side of that line should affect us, and yet it seems to. That's what makes the dark flow so strange. It suggests there may be something beyond our universe that exerts gravitational influence, a mass or structure or something even more bizarre lying outside the cosmic curtain. One idea is that our universe might be part of a larger multiverse, that just as stars belong to galaxies, our universe might belong to a cosmic landscape of many universes, each with its own space, time, and rules. And if another universe lies close enough, its gravity might leak through, pulling on ours in ways we can barely detect. Or maybe it's a pre-Big Bang structure, a remnant of an earlier cosmos that collapsed and rebounded into ours. An echo from before time, still rippling through the void. But not everyone agrees the dark flow is real. Some suggest it's an error in data, a misreading of microwave background radiation. Others say it could vanish with better measurements. Still, the question lingers. What if we're part of a much larger whole? What if our universe, vast as it is just one cell in a cosmic body, moving in ways it doesn't yet understand, pulled by limbs it cannot see? We feel this in life too. Moments when we move without knowing why. When we're drawn toward decisions, people, or places that seem guided by more than reason, a gravitational whisper from beyond our awareness, a dark flow of the soul. So tonight, rest in that mystery. Let yourself be pulled, not with fear, but with faith. Faith that even unseen forces may carry you somewhere you're meant to go. And in the quiet hum of the cosmos, drifting slowly toward the unknown, you are not lost, you are in motion. Phantom energy and the big rip. What if the universe wasn't slowing down but tearing itself apart? We once believed that gravity would win, that the expansion of the universe, the stretching of space that began with the Big Bang would eventually slow, stop, maybe even reverse. But in the late 1990s, astronomers discovered something shocking. The universe is accelerating. Galaxies are drifting away from each other faster and faster, not slower. Space itself is expanding not just steadily, but with growing speed. And the cause, we believe, is something called dark energy, a mysterious force that fills space and pushes everything apart. But even that might not be the end of the story. Some theories propose a more extreme version, phantom energy. Unlike dark energy, which causes steady acceleration, phantom energy grows stronger over time. It doesn't just push space outward, it tears at the very fabric of the cosmos, growing more intense as the universe expands. And if phantom energy is real, then the future of the universe may end in a moment of quiet violence called the Big Rip. Here's how it would unfold. First, distant galaxies disappear from view, receding faster than light can reach us. Then, over billions of years, clusters of galaxies pull apart. Gravity can no longer hold them. Then, solar systems disintegrate. Planets break from stars. Moons drift away. And as the phantom energy strengthens, it turns inward. Stars are torn from within. Atoms begin to separate. The forces that bind protons and neutrons lose their grip. Even space-time itself stretches beyond coherence. In the final seconds, everything rips. Not with fire, not with explosion, but with acceleration, a universe unzipping itself at the seams. Now, this is only one hypothesis, a speculative future. The actual fate of the universe may be gentler. A slow fade, a cold death, a rebirth. But the Big Rip whispers a different possibility, that the universe does not collapse but lets go, that the final act is not compression but expansion without limit. In life, we fear falling apart. We fear coming undone at the hands of time, of loss, of change. But sometimes, release is not destruction. Sometimes, it's the surrender of structure so that something new can form. We are held together by forces we rarely see: relationships, beliefs, identities, and sometimes those very bonds begin to stretch, to strain, to fail. And maybe, like the universe, we feel it, the slow unraveling of what once seemed solid. But maybe that's not the end. Maybe it's just a moment of profound transformation. So tonight, if something inside you feels like it's loosening, let it. Don't grip too tightly. Let the old drift away. And sleep knowing that even if the universe rips, it does so not in panic, but in grace. The axis of evil. What if the universe had a preferred direction? We're taught that the cosmos is isotropic, the same in all directions. No up or down. No left or right, just endless symmetry. A vast sea of galaxies expanding evenly in all directions from a common origin. But in 2005, something strange was found in the oldest light in the universe. A pattern, a slant, a subtle but unsettling alignment. It was discovered in the cosmic microwave background, the faint afterglow of the Big Bang, still echoing through space. When scientists mapped this radiation in detail using data from the Wilkinson Microwave Anisotropy probe, they expected randomness, chaos, a soup of tiny fluctuations with no clear order. Instead, they found an axis, a direction, a strange alignment of temperature fluctuations stretching across the sky as if the universe itself had a spine, a cosmic tilt, a preferred way to lean. They called it, half joking, half serious, the axis of evil, because it broke the rules. It shouldn't be there. If the Big Bang really birthed a uniform universe, this kind of cosmic bias shouldn't exist. And yet, it does. Some dismissed it as noise, a statistical fluke. Others said it might be a result of foreground contamination, perhaps from our own galaxy, interfering with the data. But after repeated observations from different missions, including Planck, the anomaly persisted. The axis was real, and it was strange, because it seemed to line up with our solar system's ecliptic plane, the imaginary flat surface on which the planets orbit the sun. As if the universe somehow knew where we were, as if our orientation had been burned into the cosmos at the beginning of time. That idea makes scientists deeply uncomfortable. It challenges the cosmological principle, the foundation of modern cosmology, that we do not occupy a special place in the universe, that the laws and conditions of the cosmos are the same everywhere. But what if they're not? What if the universe really does have a hidden order, a subtle preference, a cosmic bias that we're just beginning to see? It raises big questions. Is the universe shaped by something outside itself? Did something influence the Big Bang? Are we just seeing an illusion or witnessing a deeper design? And in our lives too, we ask the same. Are the patterns around us coincidence, or do they whisper of meaning? Do the alignments we notice between moments, people, choices speak of structure beneath the surface? Sometimes, meaning feels like an axis, an unseen thread, a quiet guide. So tonight, lie still beneath the sky. Let the stars spin above you. And feel perhaps that you are part of something tilted, mysterious, and deeply alive. Quantum vacuum fluctuations. What if emptiness wasn't empty at all? We imagine the vacuum of space as nothingness, a silent void. The backdrop of stars, dark, vast, and still. But at the smallest scales, reality refuses to be quiet. Even in perfect vacuum, there is motion. This is the world of quantum vacuum fluctuations. According to quantum field theory, every point in space is filled with invisible fields, fields for electrons, photons, quarks, and more. These fields don't always lie still. They vibrate even when there's no particle, no heat, no light. This isn't metaphor, it's measurable. Particles pop in and out of existence, briefly forming from energy, then vanishing. They are called virtual particles, and while they cannot be directly observed, their effects are real. One example is the Casimir effect. Place two uncharged metal plates extremely close together, mere nanometers apart, and they feel a mysterious force pulling them together, not because of static, not because of gravity, but because the vacuum between them is different from the vacuum outside. Only certain fluctuations fit between the plates. fewer than in open space. So, the pressure from the outside is greater, and the plates are pushed inward. That's quantum vacuum fluctuation in action. In essence, nothing is never really nothing. Even space that appears empty is teeming with possibility, fields bubbling with borrowed energy, a sea of flickers and half-formed existence. Every particle we know may be a ripple on this invisible ocean, and that raises strange ideas. Some physicists suggest that these fluctuations were the seed of the universe itself, that the entire cosmos may have erupted from a vacuum fluctuation, a moment when energy spiked briefly, randomly, and birthed space, time, and matter. In this view, existence is not a grand structure resting on bedrock, but a wave on a wave, born from chance, shaped by dance. And yet, it all feels so solid to us. We live among walls and roads and clocks and names, but beneath it all is a shimmer, a hum, a soft, silent quiver that never stops. Maybe that's true of us too. We think of ourselves as stable, consistent, known, but within us are flickers, emotions rising, fading, thoughts appearing, dissolving, moments of doubt, of joy, of wonder, all flickering through the vacuum of awareness. You are not fixed, you are fluctuation, and that's not chaos, it's creation. So tonight, rest in the quiet pulse beneath all things. Know that even in the dark, even in silence, even in nothing, something is always becoming. The void between superclusters. What if the most mysterious places were the ones with almost nothing at all? We often marvel at galaxies spiraling cities of stars, glowing with light and gravity and motion. But these bright structures make up only a small fraction of the universe. The rest is mostly emptiness, vast, dark, hauntingly still. These are the cosmic voids, the great gulfs between superclusters. Expanses of space that can stretch across hundreds of millions of light years, containing almost no galaxies, no stars, no dust, just a quiet breath of the cosmos. One of the largest known voids is called the Boötes Void, so massive and so empty that it's often nicknamed the Great Nothing. It spans over 300 million light years across, and within it, there are only a handful of galaxies when there should be thousands. If the universe is a sponge of matter with galaxies clustered like soap bubbles around filaments of gravity, then voids are the spaces between the threads, gaps in the cosmic web. Not accidents, but patterns. Not chaos, but silence designed by gravity. And yet, these voids are not completely empty. They are filled with dark energy, weak magnetic fields, and thin wisps of hydrogen. In their stillness, they shape the motion of galaxies around them, like valleys that channel the flow of cosmic rivers. Some astronomers believe these voids might hold keys to understanding dark energy, the mysterious force accelerating the universe's expansion. Because here, in the absence of matter, the influence of dark energy becomes more pronounced. Others have suggested stranger things. That cosmic voids may be windows tunnels through space or time. That perhaps, in places so quiet, the structure of space-time itself becomes thin, like stretched fabric. Or that some voids may be scars from early cosmic collisions, where different regions of the universe once touched. And still, others wonder, what would it be like to stand inside one? No light, no sound, no nearby stars. Just the black expanse stretching endlessly in all directions. A place where orientation means nothing, where time seems paused, where the loneliness is not sad but sublime. Because here, the universe is not shouting, it's whispering. And in that whisper is the reminder that absence has value, that silence is not the opposite of meaning, but sometimes the space where meaning grows. In our lives too, we fear the voids, moments of stillness, of emptiness, of not knowing. But perhaps those are the places where the most profound changes begin. So tonight, imagine yourself in a cosmic valley, floating gently in a sea of quiet, and let the stillness of the universe hold you, not as something to escape, but something to understand. Cold spots in the cosmic microwave background. What if the echo of creation carried a scar? After the Big Bang, the universe was hot unimaginably so, but as it expanded, it cooled. And about 380,000 years after its birth, it released its first light. That light, stretched by billions of years of cosmic expansion, still surrounds us. We call it the cosmic microwave background, or CMB. It's not bright or visible to the naked eye, but it's everywhere, a soft glow of ancient photons bathing the entire sky. Uniform, yes, but not perfect. Tiny fluctuations ripple through the CMB like subtle waves in a calm ocean. These temperature differences, 1 part in 100,000, seeded the galaxies, the stars, the structures we know today. But then there's one anomaly that stands out. A large, puzzling cold spot. Discovered by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, this region of the sky is significantly cooler than the surrounding CMB, too large and too cold to be explained by standard models of inflation or quantum randomness. This cold spot spans hundreds of millions of light years across. It's real, it's measurable, and no one fully understands why it's there. Some believe it's caused by a supervoid, a massive, underdense region of space lying between us and the CMB, distorting the light through a phenomenon called the integrated Sachs-Wolf effect. The idea is that photons passing through the void lose more energy than expected, creating the appearance of a cold region. But the supervoid theory doesn't fully account for the size and temperature of the anomaly. Others wonder if it's something deeper. A collision with another universe, perhaps. A fingerprint from the multiverse. A scar left when our universe brushed against another bubble during cosmic inflation. Or maybe it's something we haven't even imagined yet, something fundamental. The cold spot challenges our sense of order, a whisper from the birth of time that says, something unexpected happened here, and in a strange way that's comforting. Because even the cosmos, with all its symmetry and elegance, bears imperfections. Slight deviations, scars, and yet it thrives, expands, evolves. We too carry cold spots, places in our stories where something unexplainable happened, a sudden loss, a quiet trauma, an emptiness that lingers. But like the universe, we keep going. We don't erase the cold spot, we integrate it. We learn to carry it gently, with wonder instead of fear. So tonight, imagine yourself wrapped in ancient light, a soft glow from the birth of everything. Let your own cold spots be part of that glow, and sleep knowing that even the scars of the cosmos are just another kind of beauty. Galactic conformity. What if galaxies copied each other's behavior, even from afar? In the grand structure of the cosmos, galaxies are like islands floating separately in a vast dark ocean. Each one billions of stars strong, spinning, colliding, evolving on its own terms. And yet, something strange has been noticed. Galaxies seem to imitate each other. Even when separated by vast distances, their star formation rates, colors, and types tend to align in patterns that don't quite fit our current models. This is called galactic conformity. In its simplest form, it means that galaxies in the same cosmic neighborhood, even if they aren't directly interacting, tend to behave similarly. Spiral galaxies birth stars together. Ellipticals go quiet in sync. It's as if they're keeping cosmic pace linked by some unseen thread. Theories try to explain this. Maybe it's shared gas reservoirs, invisible streams of hydrogen flowing through cosmic filaments, feeding galaxies in unison. Or perhaps it's halo assembly bias, where galaxies forming in the same dark matter structures inherit similar properties. But those theories can't explain all of it, because conformity sometimes shows up over tens of millions of light years too far for gas to travel, too distant for gravity to influence directly, which leads to deeper, stranger questions. Could there be hidden forces, subtle fields that guide galactic behavior across incomprehensible distances? Could the cosmic web, the massive sponge-like structure of the universe, transmit influence not just through mass, but through some kind of information flow? Or maybe galaxies simply evolve in rhythm because the universe at its deepest level is coherent, interconnected, not just in mass, but in story. We see this in nature all the time. Trees in a forest growing in sync, responding to climate and soil in silent cooperation. Fireflies blinking together without a leader. Or flocks of birds turning as one not from planning, but from shared intuition. What if galaxies are no different? What if the universe breathes through its structures, pulses through its clusters, sings through its stars? And in that breath, even distant islands learn to move together. Maybe we're not as isolated as we think. Maybe you too are influenced by people you've never met, moments you've never noticed, a synchrony flowing underneath your awareness. Call it resonance, call it gravity, call it mystery. But it's there, that quiet harmony of the universe, rippling through the void. So tonight, let yourself relax into that rhythm. You are not alone, you are not separate. You are part of a chorus of galaxies, of minds, of quiet, dancing motion. And in the stillness of your sleep, you are humming in tune. The time dilation at the edge of black holes. What if time could almost stop? Black holes are often described as monsters, places where gravity becomes so intense, nothing escapes, not even light. But beyond their power to consume, black holes also warp something deeper. They distort time. This isn't science fiction. It's a fundamental prediction of Einstein's theory of general relativity. As you approach a black hole, time itself slows down not just subjectively, but physically, measurably. The closer you get to the event horizon, the boundary beyond which nothing returns, the slower time flows for you compared to someone far away. This is called gravitational time dilation. Imagine a spaceship hovering just outside a black hole's event horizon. To the crew on board, time feels normal. A minute passes like any other. But to someone watching from afar, perhaps orbiting at a safe distance, that minute stretches. 5 minutes, 10, 1,000 years. From the outside, it looks like the crew has almost frozen in place, suspended forever at the edge of darkness. And if they fell in, they'd cross the horizon in their own time, feeling only a gentle tug until the singularity awaits. But to us, watching, they'd never quite vanish. Their image would redshift, fade, and smear across eternity. That's the poetry of black holes, not just their hunger, but their manipulation of experience itself. Time, which we think of as steady and universal, becomes fluid, shaped by space and mass. Bent and stretched like taffy by gravity's hand. This isn't limited to black holes. Even Earth's gravity slows time just a little. Your head ages slightly faster than your feet. A clock on a mountain ticks quicker than one at sea level. But near a black hole, that effect becomes cosmic, infinite, and it leads to one of the most haunting ideas in modern physics. That, in theory, we could use this time distortion to peek into the far future, hover near the edge of a black hole for a few hours, and return to a universe that has aged billions of years. A portal to tomorrow, or an eternal pause at the edge of everything. In our own lives, time feels relentless, always moving, always slipping. We try to control it, fill it, outrun it. But maybe time isn't as rigid as it seems. Maybe we carry black holes inside us, moments so heavy with emotion, with memory, with meaning that they warp our experience of time. A minute in grief feels like an hour. A second in joy, like nothing at all. So tonight, let the ticking slow. Let your mind hover gently, just outside the event horizon of sleep, where time stretches, where thoughts fade, and where the quiet pulls you, not into terror, but into stillness. Rogue planets drifting in darkness. What if a world had no sun to call home? We imagine planets orbiting stars like Earth dances around the sun, warmed by light, anchored by gravity, part of a system. But not all planets are lucky enough to belong. Some are wanderers, lost, unbound. These are the rogue planets' worlds adrift in the blackness of space, orbiting nothing. They are not rare. In fact, there may be billions of them in our galaxy alone. More planets without stars than stars themselves. But how do planets end up alone? There are two main possibilities. Some rogue planets may have formed like stars directly from collapsing clouds of gas and dust, never gathering enough mass to ignite into starlight. Others were likely kicked out, born in star systems like ours, but ejected by chaotic gravitational interactions. Imagine a young solar system planets forming, colliding, shifting. One massive world swings too close to a neighbor or a passing star and gets flung into the void. Suddenly, it is alone, no sun, no warmth, just endless night. And yet, they endure. A rogue planet can drift for billions of years, silent and unseen, wrapped in darkness. Some may have thick atmospheres that trap internal heat. Others may harbor liquid oceans beneath frozen crusts, warmed by radioactive decay in their cores like Jupiter's moon Europa. But on a planetary scale. And here's the strange part. Some may support life. Not life as we know it, dependent on sunlight and seasons, but life that thrives in darkness. Deep beneath ice, in oceans warmed from within, shielded from radiation by miles of crust. A hidden biology. A secret evolution. Entire ecosystems we may never see. We've detected a few rogue planets through gravitational lensing, the brief bending of starlight as they pass in front of distant suns. But most remain invisible, no light to reflect. No orbit to betray their presence. They are the ghosts of creation. And yet, they may outlast the stars. When the universe grows cold and the lights go out, rogue planets will still be drifting, quiet, untouched, carried by inertia across a frozen sky. There's something beautiful in that, a reminder that belonging isn't always a matter of orbit, that even alone a world can survive, a world can glow from within, and perhaps so can you. We are taught to find our center in others, in relationships, in systems, in suns, but sometimes we drift, sometimes we are cast out, and sometimes in that drifting we discover ourselves. So tonight, imagine a planet drifting gently through the dark, no sun, no sound, only a steady, quiet warmth deep within, and know that you, too, carry that glow, even in the loneliest spaces. The mystery of Tabby's star. What if a star flickered like no star should? Stars are usually predictable. They pulse. They brighten or dim in patterns we can study, chart, and explain. But sometimes something breaks the rhythm. Something refuses to behave. And one such mystery is Tabby's star. Also known as Kick 8,462,852, this star is located about 1,470 light-years away in the constellation Cygnus. From a distance, it looks ordinary, an F-type main sequence star, slightly bigger and hotter than our Sunday. But in 2015, astronomers noticed something strange. The light from Tabby's star wasn't stable. It dimmed, sometimes a little, sometimes a lot. And not in a smooth, cyclical pattern like a variable star, but erratically, deeply, and unpredictably. Some dips in brightness were up to 22%, far more than what a planet transit or dust cloud could explain. This wasn't a simple eclipse. It was a mystery, and as scientists scrambled to explain it, one idea captured the imagination of the world: a megastructure. What if the dips were caused by an alien civilization building something massive around their star? A Dyson swarm, perhaps a collection of solar harvesting satellites designed to collect energy. Not a solid shell, but an uneven cloud of machinery casting irregular shadows. The idea, though speculative, was taken seriously enough to be published. It even led to search for extraterrestrial intelligence, SETI teams aiming their instruments toward Tabby's star, listening for artificial radio signals. They heard nothing, and yet the mystery remains. More grounded explanations emerged: clouds of interstellar dust, swarms of comets, remnants of a shattered planet, or large, irregular disks of debris. Some of these could account for certain dips, but not the largest ones. Not the long-term dimming that has also been observed over decades. Tabby's star still flickers, without a clear reason. It's like watching a lighthouse through a fog where the pattern of light never repeats, never settles. Just a series of winks and shadows from something we can't quite see. And maybe that's the point. The universe is not required to explain itself. Some stars will flicker without telling us why. Some stories will stay incomplete. In our own lives, we crave patterns, clear arcs, tidy answers. But life, like light, often dips without warning. Not because something is broken, but because something unknown is passing through. A memory, a fear, a shift in mood. It doesn't always make sense, and it doesn't have to. So tonight, imagine Tabby's star blinking slowly across the void, unrushed, unapologetic, unsolved, and feel the comfort in that mystery. The grace of not knowing. The beauty of a question that shines even in silence. Intergalactic gas streams. What if galaxies were not as separate as they seemed? From far away, each galaxy looks like its own isolated swirl, an island of stars floating through darkness. But between these luminous giants, something invisible connects them: rivers of gas. These are the intergalactic gas streams, enormous filament-like flows of hydrogen and helium stretching across the void, linking galaxies together like strands in a cosmic web. They are thin, diffuse, and cold, but colossal, and they are real. We cannot see them with regular telescopes. They emit no light of their own. But astronomers have found clever ways to detect them by using quasars. Quasars are distant, brilliant beacons powered by black holes. When their light passes through intergalactic gas, it gets absorbed in specific patterns. These absorption lines are like fingerprints, revealing the presence, motion, and structure of the hidden streams. What we've found is stunning. These gas filaments stretch across hundreds of millions of light years, forming highways of matter through which galaxies move, grow, and feed. They are the veins of the universe, and galaxies are just the bright cells carried within them. Even our Milky Way is connected. It's not drifting alone in black emptiness, it's swimming through currents, gently sipping gas from surrounding filaments, fueling star formation, exchanging whispers with the cosmic sea. Some of these streams are hot, glowing faintly in X-rays. Others are cold, barely above absolute zero. Some move slowly, others race like wind. Some collide, creating shock waves that ripple through clusters. And in places, these filaments meet. They intersect in nodes, the densest regions where galaxies form in abundance. These nodes become galaxy clusters, the bustling cities of the cosmic web. But the mystery doesn't end there. Some simulations suggest that dark matter follows the same patterns, forming invisible scaffolding around which gas collects. If true, then these filaments are not just streams of gas, but outlines of the deeper, unseen structure of everything. Imagine it. An invisible network stretching through the universe, guiding galaxies, shaping matter, whispering order into the chaos. It changes how we see isolation. Because even in the loneliest stretches of space, connections remain. Even when galaxies appear to drift alone, they are linked by forces they cannot see, by currents they cannot resist. We too float in such unseen streams, in family lines, in histories we never lived but still carry, in the moods of those around us, in the quiet gravitational pull of relationships that shape who we are. Even when we feel separate, we are part of something vast. So tonight, let yourself drift, not alone, but held by invisible filaments of connection and care. The quiet gas between galaxies, the soft forces between hearts, the flow beneath everything. White holes, the opposite of black holes. What if the universe had places where nothing could enter, only escape? We know black holes, we fear them. Regions of space where gravity is so intense that not even light can flee. Places of no return. But lurking on the edges of theory is something stranger, something inverse. The white hole. Where a black hole pulls everything inward, a white hole does the opposite. It pushes everything outward. No matter can enter, no energy can cross its boundary. It is a cosmic one-way valve, but in reverse. A place where time runs away, never toward. White holes are not observed. Not yet. They are mathematical possibilities, solutions to Einstein's field equations that mirror black holes in reverse. For every collapse, perhaps an eruption. For every sink, a source. The idea becomes even stranger when tied to the concept of wormholes, theoretical tunnels through space-time that connect distant regions or even different universes. In some models, one end is a black hole and the other a white hole, a throat of space-time, drawing in from one place and spitting out into another. But white holes come with paradoxes. If they exist, why don't we see them? Where are the bursts, the boundaries? One theory suggests that white holes may be connected to the Big Bang itself, that perhaps the universe began as a kind of white hole explosion. An event where all matter, all energy, all time emerged from a single point, but from the other side of something that once collapsed. Another theory proposes that black holes become white holes. That after unimaginable spans of time, when a black hole evaporates through Hawking radiation, it transforms, releasing all that it once consumed in a final, spectacular outburst. A cosmic exhale after an eternity of holding breath. But we don't know. White holes remain theoretical whispers in the equations, unconfirmed by the stars. And yet, they offer a strange hope, that not everything is about collapse. That some singularities are not prisons, but passages. That some deaths lead not to endings, but to rebirths. We feel the pull of black holes in our lives, those dark moments where everything seems to fall inward. Grief, loss, silence. But what if, on the other side, something bright awaits? A moment of release, a burst of meaning, a new beginning. So tonight, as your thoughts drift, imagine a white hole glowing in the darkness, not devouring, not trapping, but giving, endlessly. A reminder that even the void has a voice. And sometimes it sings in reverse. The axion, a particle that might make up the universe. What if the most important thing in the universe is something we've never seen? All around us is matter, stars, planets, people. But there's something more, something invisible, undetectable, yet vastly more abundant. It's called dark matter, and we don't know what it is. It doesn't shine, it doesn't absorb, it doesn't reflect, but it pulls. It tugs on galaxies, shapes cosmic structure, bends light in subtle ways. It's there, and it accounts for nearly 85% of all matter in the universe. But what if this unseen mass is made of a ghost? Not a spirit, but a particle. A strange, whispering thing called an axion. The axion was first proposed not to explain dark matter, but to solve a different mystery in particle physics, a problem with why strong nuclear forces don't violate certain symmetries. It was a quiet fix, an elegant patch. But then scientists realized something astonishing. Actions, if they exist, could be dark matter. They would be extremely light. They would barely interact. They would drift through the cosmos, through stars, through us, unnoticed. Trillions may pass through you every second, like wind through empty streets. We haven't detected axions directly, but scientists are trying. Experiments like ADMX and Casper aim to spot them indirectly through magnetic resonances, through subtle flickers in fields, through tiny disturbances in space. It's like listening for the sound of a snowflake landing, delicate, almost silent, but possibly everything. Because if actions are real, they change the story of the universe. They explain its hidden mass. They reveal why galaxies hold together. They become the quiet scaffolding of everything we see. And they teach us a deeper lesson that the most powerful things may be the least visible, a soft force that doesn't shout, a presence that never demands notice, a ghost particle that shapes galaxies not with fire but with restraint. We live in a world obsessed with the visible, the loud, the brilliant. But in the universe, it is often the subtle that carries the most weight, like love that doesn't announce itself, like kindness that expects no reward, like silence that speaks louder than noise. So tonight, as you close your eyes, imagine actions drifting all around you through walls, through stars, through centuries of time. Gentle, patient, hidden, and yet holding up the cosmos. The Eridanus supervoid, an empty scar in the cosmos. What if the universe had bruises? Across the night sky, the cosmic microwave background, the afterglow of the Big Bang glows softly in every direction. It's nearly uniform. Nearly, but not perfectly. In one patch of the southern sky, in the constellation Eridanus, there's a strange cold spot, a region where the microwave background is significantly cooler than its surroundings, cooler than it should be. And it stretches across a region 1.8 billion light-years wide. This is the Eridanus supervoid. A supervoid isn't truly empty, it's just a region with far fewer galaxies, far less matter than average. But this one is unusually vast. A desert in the universe's grand forest. A hole, not in space itself, but in structure, and it's not supposed to be there. According to standard models of cosmology, voids of this size are extremely unlikely. They shouldn't form naturally in a universe that spreads out matter relatively evenly over vast scales. Yet here it is, chilling the light from the Big Bang as it passes through. But how does emptiness make light cold? It's called the integrated Sachs-Wolf effect. As light travels through a gravitational well like a cluster of galaxies, it gets slightly blue shifted going in and red shifted coming out. In balance, the effects cancel out. But if there's a void, the shift isn't even. Light exits slightly cooler. It's a tiny change, but across such a vast region, it becomes noticeable. Some scientists question whether the Eridanus supervoid alone can explain the cold spot. Maybe it's something deeper, a remnant of an ancient cosmic string, a ripple from another universe, a scar from before time had rules. It remains one of the great puzzles of observational cosmology. A void, silent and immense, imprinted not just on space, but on time. And it invites us to ponder what emptiness really means. We think of space as full of stars, light, gravity, and fire. But so much of the cosmos is absence. So much of reality is what's not there. And that absence has weight. It shapes the journey of light. It alters the rhythm of time. It leaves marks that last for billions of years. In our lives, too, the voids matter. The spaces where something was supposed to be. The friendships that faded. The paths never taken. The quiet stretches between memories, we try to fill them, but sometimes they simply remain, and still they shape us. So tonight, imagine the Eridanus supervoid stretching across the sky, a billion light-year whisper of quiet. Let its silence remind you, That emptiness, too, is part of the story. That space to breathe is sacred, and that even the universe holds room for the things it cannot hold. The red rectangle nebula. Geometry in the stars. What if a star could draw with rulers? Most nebulae are wild, swirling, irregular, chaotic clouds of gas and dust sculpted by stellar winds and supernova explosions. But in a quiet patch of the sky, something astonishing appears. A shape, a rectangle. This is the Red Rectangle Nebula, an extraordinary symmetrical formation located about 2,300 light-years away in the constellation Monoceros. And unlike the familiar whorls of Orion or the butterfly wings of planetary nebulae, this one presents a mystery in perfect lines. It looks like a glowing red box. Not soft or undefined, but framed with right angles, rungs, and sharp edges that feel almost artificial, as though geometry itself had been etched into the sky. At its heart is a dying star, more precisely, a binary system. Two stars orbiting one another closely, one of which is shedding its outer layers as it approaches the end of its life. The gas it releases isn't sent out randomly. Instead, it forms bipolar outflows, twin cones of matter stretching away from the center, funneled by a dense disk of dust around the stars. And because we happen to view the system edge-on, the overlapping cones create the illusion of a rectangle, a celestial origami folded in light and shadow. Its red glow comes from hydrocarbon molecules, fluorescing under ultraviolet radiation, complex chemistry, delicate balance, stark structure. It almost doesn't seem real. And for years, scientists questioned whether such a precise form could naturally emerge. Could chaos birth order? Could dying stars produce architectural clarity? The red rectangle answers, yes. Even in collapse, there is beauty. Even in death, symmetry. Its rungs, like a ladder rising into space, might be shocks or waves in the outflow. Its corners, illusions of perspective, but its mystery lingers. We don't often expect shape from the stars. We expect explosion, entropy, noise, but the universe isn't just wild. It's also patient, capable of structure, capable of grace. And it reminds us that not all endings are chaotic. Some are composed. Some burn out in patterns. Some draw poems in red light. In our own lives, we fear unraveling, disorder, the fraying at the edge. But maybe, like the red rectangle, even our falling apart holds form. Maybe the geometry of a soul is revealed not in its stability, but in its letting go. So tonight, picture the red box in space glowing gently, impossibly symmetrical, floating in darkness. Let its calm lines hold you. Let its precision soften your mind. And remember, even stars die beautifully. The zone of avoidance. What lies behind the Milky Way? What if there was a place in the universe we simply couldn't see? When we look out into the cosmos, we imagine that our telescopes can peer in every direction across billions of light years, through time itself, to the birth of stars and galaxies. But that's not entirely true. There's a blind spot in the sky, a band where galaxies vanish, light fades, and data goes quiet. This region is called the zone of avoidance. It stretches across the plane of the Milky Way, a wide, dense swath where our own galaxy gets in the way of our view. The problem isn't distance. It's dust. Interstellar dust and stars within our galaxy obscure the light coming from beyond. Like trying to see the horizon through a thick curtain, we know there's something out there, we just can't see it clearly. For decades, astronomers simply skipped over this zone, charting galaxies around it, building maps of the universe that had a giant gap, like a missing puzzle piece at the center. But curiosity never sleeps. What if something enormous is hidden behind the curtain? What if a superstructure, a massive galaxy cluster, or something stranger lurks behind the glow of our Milky Way? In recent years, scientists began to peek through. Using infrared and radio waves, which can penetrate dust more easily, they've started detecting galaxies hidden within the zone. And what they found is astonishing. An immense structure, a cluster of galaxies possibly linked to the Great Attractor, a gravitational anomaly pulling the Milky Way and its neighbors in a slow cosmic drift. It suggests we're not just spinning in place. We're being drawn, pulled toward something vast, something we can barely see. The zone of avoidance may not be empty, it may be hiding part of the very reason our galaxy moves, and that's the strange beauty of blindness. Just because we can't see something doesn't mean it isn't real. Sometimes the most powerful forces are the ones beyond our sight. We move through the world, guided by things we cannot name: intuition, love, memory, gravity, the pull of people we've lost, the echo of paths we didn't take. There are zones of avoidance in us too, parts of ourselves we don't fully explore, feelings tucked behind the clutter of daily life, questions left unanswered, but they're there, waiting behind the dust. So tonight, as you drift into sleep, imagine staring at the Milky Way, not just into it, but through it. Let the light of hidden galaxies shimmer behind the stars, and feel the pull of the unseen, the quiet tug of mysteries just beyond the veil. Epilogue: the quiet between the stars. What if the universe was not trying to be understood, only witnessed? We have wandered through 100 mysteries, from black holes to bright rings, from voids to whispers of particles that may never touch us. We've followed light, we've followed darkness, and we've learned that space is not empty. It is alive with questions. But tonight, as we close this voyage, perhaps it is not the answers that linger, but the feeling, the vastness, the silence, the sense that we are small and somehow still part of it all. The stars do not need our understanding to shine. They simply do. Galaxies do not ask to be mapped. Voids do not beg to be filled. They exist calmly for billions of years, changing slowly, drifting apart, holding mysteries not to frustrate us, but to remind us that wonder is eternal. And maybe that's the lesson. The universe is not a puzzle to solve, but a presence to sit with. Its anomalies, its cold spots, its glowing rings, its strange flickers are not errors. They are poetry. They are the natural rhythms of something older, quieter, and more patient than we are. Something that does not rush. So wherever you are now, lying under your own sky, know this: you are stardust folded into thought, a ripple in a galaxy's edge, a witness to a universe that will outlast every word you speak and still welcome your gaze. Let it humble you. Let it comfort you. Let it lull you into rest, because even as you sleep, the stars continue their slow, silent dance. And somewhere out there, a mystery unfolds, just for the sake of being beautiful. Good night, traveler. The cosmos is holding you,